First of all, I would like to thank you all, to thank the organizers, so Angela, Evelina, Colin, Nicolas, Rinat, for organizing this event, also for inviting me to give this lecture. So my lecture will be a kind of introduction to the fact that there is a relationship between topological recursion and two-dimensional conformal field theory. We have already made several papers about that. I will try to give you just a glimpse of that. So this is the sketch of my plan, which might change a little bit in the 3 days, but I will start by an introduction about the subject. In fact, I will insist on notations, because maybe I don't know our backgrounds. Well, in fact, this first part of introduction may seem very trivial for some of you, only things that you know very, very well. And you may wonder why I'm doing that. And basically, I'm doing it for those who don't know. And in fact, I already tried to give this lecture in the past, and people who didn't have a background in this CFT field were just puzzled by notations, with brackets, with operators. And people basically got stuck there. So that's why I want to insist on that. So topological recursion is a procedure. Now why is there a relationship between these two subjects? Conformal field theory is something that comes from physics. It's a field theory. So basically you have particles, or in fact people say states or operators that interact. You want to measure how they you want to make predictions of interaction between these particles and everything. And on the other side, you have topological recursion. Topological recursion is a procedure that takes a spectral curve, which is basically an algebraic curve with some extra structure that we will talk about. And topological recursion is a recursive procedure. So basically, this is the input. This is somehow the initial condition of a recursion. And by recursion, you produce many other things labeled by two integers, g and n. And they are n forms on the surface of the spectral curve. And why does it have anything to do with CFT? That's what I'm going to try to explain. So there is naturally a spectral curve associated to a CFT, to this CFT. And when you do that, you will produce some sequences of forms, and you can use them as you can make series out of these coefficients. And these formal series are hopefully the asymptotic expansion of the CFT in some limit. So in the CFT, we will have, so in the heavy limit, which means larger charges. So basically, you will scale every charge to 1 over h bar alpha I, and you want to compute everything. You want to compute everything as h bar expansions. So all correlation functions in the CFT, you would like to compute them as series in small h bar. In small h bar expansion. And it turns out that the coefficients will be those given by TR. Okay, so this is basically what this is about. Here I wrote a small crash course on Lie algebras for those who don't know. Maybe I will leave this board somewhere because we will need the notion of Cartan algebra. So let me just be very brief. In fact, the Lie algebra, the Lie group that I will mostly look at is the SLQC is SLQC, so basically Q by Q matrices of determinant 1. Its Lie algebra, so tangent space at identity, is Q by Q matrices with trace 0. The Cartan algebra is a commutative, is the maximal commutative subalgebra in it, and so it will be the diagonal matrices Q by Q with trace 0. It is known, well, there is a famous corpus of things about Lie algebras. It is known that there is a canonical way of decomposing the Lie algebra as Cartan plus root spaces. And what are roots? Roots are somehow eigenvalues. So, I mean, since elements of the Cartan algebra commute, they are adjoint. I mean, when they act as a commutator, they are endomorphisms of Lie algebra, and since they commute, they have common eigenvectors. And basically, the roots are the eigenvalues of the common eigenvectors. So this is, and then you can decompose the Lie algebra into Cartan plus these eigenspaces. Okay, all that is well known. In the SLQC algebra, if an element of a Cartan is written as diagonal of H1, HQ, okay, whose sum is 0, because trace is 0, then roots are just the linear forms that to an H associate Hi minus Hj. It is also, if you see that alpha Ji is minus, minus alpha ij is alpha Ji, which is also a root, and it's always possible to put half the roots and call them positive and half the roots call them negative, and the simple roots are the positive roots that you cannot write as sums of positive roots. And the number of them is always equal to the rank of the Lie algebra, which is the dimension of the Cartan. So this is just a very small crash course, because now let's start with the setting of what. So we want to do a 2D CFT, but on a surface, a Riemann surface. Sigma 0. And very often I will take sigma 0 to be just the Riemann sphere CP1, which is just C plus the point at infinity. So there is a canonical coordinate on it. So this is, so I will need a Riemann surface. I will need a Lie group. In principle, you can take a reductive Lie group, but it's simpler if you take a semi-simple Lie group and even a simple Lie group. And in fact, I will take, in most of my example, I will take SLQC, but very often I will state the results for arbitrary Lie groups. Okay, right. Okay, sorry, and I will also, in this first lecture at least, and I don't know in the others, I will do a 2D CFT with 0 background charge. I can also do the non-zero background charge, but it's much heavier. I mean, basically everything works more or less the same, but the computations are much more complicated, much more involved. And then there is a formula for this series which relates so basically so it corresponds to having the central charge, which will be the rank of the Lie group. Okay, sorry. Okay, so now let me go to the introduction of what we want to do. Well, in physics, what you want to do is to be able to measure get things. So you want to have a theory that you can compare to experience, and you want to have to measure quantities. They are often called correlation functions, or in fact, basically, typically the probability of observing certain particles in certain positions. Well, and probabilities are real positive numbers. And they should be non-ambiguous. So basically, you would like to have some functions, let's say some functions of having that will depend on certain number of variables. Let's call them zeta 1, alpha 1, zeta 2, alpha 2, and so on. Basically, this will be somehow the probability of having well, in fact, let me call them for the moment particles of charge alpha I at position zeta I on sigma 0. Whatever that means. It should be a function, so something non-ambiguous. Something, if I give you the position of the charges, I get a positive real number. This is the dream of what you would like to do in physics.
Just one question. What is the background charge in the general CFT?
It can be anything. I mean, you choose it.
My choice won't please you, but how do you, what is it? I know the central charge, but what is the background charge?
Okay, you mean what is the meaning of a background charge? Okay, let's ask. There are many specialists in the room. Well, somehow this is the. I think this is the charge you want to put at infinity to cancel some things.
But it's okay. My question is, if I am given a GFF, I know what is the background charge. Yeah. But if I have a general CFT, what is the?
In fact, let's discuss this after. For me, I'm just. What I mean by that is just I will consider a special type of CFT. I think there are many people here that can answer this question better than me. But I will just put myself in a special setting where computations are easier. Just take it like that. I mean, basically this remark in parentheses was just for specialists. But we can discuss that later. But in principle, Q is something you could choose as you wish, is a value you could choose as you wish. But computations are simpler if you take it 0.
Will you take it complex?
I think so, yes. Yeah. So, in principle, this is the dream of what you would like to get in physics. It's to really have a measurable function. And I insist on function because later we'll have multi-valued function, but in physics you would really like to get a mono-valued function. What is really called the function? So in fact, on particles, in fact, I will replace this word by states, or in fact by operators. I mean, they are not really particles. Now, you know that in quantum theory, very often probabilities are the square norm of some other functions, zeta 1, alpha 1, okay? Modulus square. And when you do that, in fact, now you get complex functions instead of real positive functions. So basically what you would like to compute in physics are more like functions of complex functions, more like complex functions. Then they might not be monovalued. They might have some ambiguity, in particular the phase, but they might have more complicated ambiguities. And in fact, the right way on, and since we are in a conformal field theory, you can guess that something will have to be analytic, so complex and analytic. And in fact, the idea is that we will look for functions that are complex, locally analytic functions, and this is what we, by taking somehow the square norm, we will get our probabilities. But in fact, you cannot really do just the square of a function. That won't work because these functions, these locally analytic functions which will be inside are not monovalued. They are defined only on the universal cover, and they may have monodromies, and in fact you have to combine them together. So in fact, more generally, what you would like to do is to write your f as a sum over a basis, with some coefficients, f eta of your variables times f eta prime of your variable complex conjugate. Okay, so that's typically that. So in fact, what we are looking for now is just not one function of the position on charges, but a basis of functions that are locally analytic and that under monodromies they get mixed together. So you should look for such a basis. And if you want the f to be real positive, so f real implies that c eta prime complex conjugate should be c eta prime eta, I think. So basically C is a Hermitian matrix. And if you want f to be monovalued, it means that under monodromies, so when the positions turn around each other, the zeta i's go around each other, you would like that f becomes a linear combination of other f's, and the coefficient c should cancel the monodromies. I will not write in details what it is, but basically you should find the c's that cancel the monodromies. And then you have a good physical observables. And now, how are we going to find, and so these things which are analytic in the variables, in the positions, these are what I shall call conformal blocks. Okay. So they are basically a basis of functions that allow you to construct all your physical amplitudes. And they are locally analytic. Now, how do we compute them? To compute them, well, in principle, for field theory, you could do things as class integrals, you could do, but this is not well defined in mathematics. You could try to define a Hilbert space with some operators satisfying some properties. But this is again quite hard to do in mathematics. And there is another way, which is axiomatic, which is the bootstrap axioms. So, in fact, instead of recomputing these functions from first principle, we shall put all the requirements we want them to satisfy and, as axioms, and we shall ask the question, can we find a set of functions that do satisfy all the axioms? And this is the idea of bootstrap axioms. You know what bootstrap means? A bootstrap is I don't have boots, but somebody has boots. It's a strap. And bootstrap is an expression in English which just says you can go up by pulling your boot up. Okay. So basically you start from nothing and you are able to raise yourself up just by pulling on yourself. This is what bootstrap means. What are the bootstrap axioms? The bootstrap axioms are related to how these functions should behave. And one of the bootstrap axioms, in fact, I've already more or less written it, is that it is possible to find such a basis such that you will find monovalued amplitudes. And this is related to, let me write it crossing symmetry. In fact, sorry, I forgot that there is a simpler even bootstrap axiom. No, sorry. Actually, before I go to the bootstrap axioms, let me go to the notation. In fact, we have several types of particles, or if you want, several types of operators in the theory. And instead of writing the function f of all the variables, physicists are used to use another notation. They use a bracket notation. Typically, the particles that are of type vertices so this is a certain type of operators that are called vertex operators. There is another type of operators which I will call currents. And let me write them this way. There are other types of operators that are called, let's say, stress energy tensor, T of x, and so on. Okay, and this bracket is just a notation to say that it is a function of all the variables that are inside. It is just take it as a notation. And this notation is convenient because when you write f somehow, you don't really know what type of particles you are talking about. Here, this notation is convenient because it tells you, it gives you information about the behavior you want to have. Typically, when zeta 1 is close to x1 or zeta 1 is close to zeta 2. And basically, this way of notation is much better to remember how this function should behave.
What are E and E1?
I will come to that in a moment. So this is just to say that instead of using the notation of functions, we use this bracket. It just means the same thing. By definition, a bracket is just a function of all the variables that you have inside. And if since conformal loss form a basis, this also depends on some index of a basis, which I will call it eta for the moment. Whatever that means, it is a function that is locally analytic in its variables. And you want to determine, and so the bootstrap axioms so there are rules that all these functions should satisfy. One of them, is linearity in the operators, so symmetry. So basically, which means that basically this does not really matter in which order you put the operators, at least maybe up to a phase. Typically the j's can be exchanged without a phase, but the v's, there could be a sign or a phase, because in fact they are fermions. So symmetry and linearity. So which means that if you take linear combinations, if you put a linear combination inside the bracket, then this is the linear combination of brackets. So this one is kind of triggered. So there is a crossing symmetry. I will not talk too much about that, but basically this is the idea that by mixing these things on their complex conjugate together, you can make a real function, monovalue. I'm not going to spend too much time on that because I will want to spend more time on two other and OP. I will spend most of my time talking about these two things. Word identities have to do with the fact that you want the conformal symmetry in your theory. And you know by another theorem that symmetry is associated to well, okay. I mean, basically this is the Noether theorem applied to a conformal symmetry. But in the end, it will give you some properties of these functions that have to be okay. This will be some analytic requirements on these functions, and I will come back to that later. I will explain in more details what they are. The OPs these are the idea of locality. So basically, this is the conformal space. And the OPs have to do with locality. Well, which is the idea that particles interact only when they are in contact. And somehow, in the real way, it would be delta function, but the equivalent, the analytic function counterpart of delta function is a simple pole. You may, okay. But basically, look, the OPs will be a condition on, so whenever two of these variables come close to each other, you have typically poles. So, yeah. So these analytic functions will have poles. And this is what it is about. So now I'm going to write precisely what are these bootstrap axioms in our setting. I will write precisely what they are. And just let me say something first, is that, okay, we have a certain number of axioms, and the question is, can we find a set of functions like that, of all possible functions like that do satisfy all the axioms? Is it possible? Does it exist? And then another question is, do the axioms are sufficient to actually compute these functions, compute the correlation functions? Are they sufficient to compute everything you want? And the answer, in fact, is yes. In fact, the axioms are so constraining that you can compute everything. Thanks to the axioms, you can compute everything you want. The issue is more about existence of a solution to the axioms, existence of a model, because in fact they are so constraining that they are over-determined. The axioms are so strong that they give you a way to compute any amplitude, but in several ways. You can, you can compute the same amplitude by using the axioms in different ways, and this will give you the same amplitude. But will you always get the same result using different methods to compute the amplitude? So basically, the question in mathematics, it's a problem of logic. Are the axioms consistent? Or another way to say that, does there exist a model for these axioms? And in fact, the answer is yes, and there are many ways to prove. I don't know if the answer is always proved. I'm not sure that it is proved in all cases. I think it's not. But at least in this setting, you can see the idea is that TR will give you as a model in terms of power series. In fact, and there are other ways to get models, but basically the idea is you will get models. Or another way to get a model, for example, is using, as you said, the Gaussian free field. This is another way to get a model in some cases, but basically, is there something that obeys all the axioms? This is sometimes an open question. Basically, is the CFT well defined? Okay. So this was my introduction. And now let's enter more
So may I ask a question? So I'm not sure my question is extremely well defined, but what you describe here is something that many people will recognize as a structure that you can get by solving some concrete models.
Yeah.
And now you are you're sort of climbing up a very high abstract tree and saying, okay, let's put some axioms and say that things have this structure. Will you be able eventually, if you find some solutions, to climb down that tree and say, then this describes this?
That's the idea.
Okay, good.
I went to this abstract level mostly to introduce the notations. So these notations as brackets are not familiar to everyone.
Yes, sir. What is the most restricting condition? Crossing symmetry or?
Crossing symmetry is a very restricting condition, and also it's the less trivial because the others are more. Well, basically the word on OPE are quite kind of trivial. And in fact, topological recursion trivially satisfies these two. But crossing symmetry is much well. Or another way to say that these two equations can be easily written as a formal series. But the crossing symmetry is involves a non-perturbative part. Crossing symmetry, you really need, it's more a relationship between Trans series and wall crossing formula about Trans series and all that. I mean, it's much more difficult indeed. So, to go further, I need to first answer your question, Leonia, which are what are alpha i's, what are e i's, and all that. So, when I write, so I'm still in the notations. When I write V alpha of zeta is a point on sigma 0, and alpha is a charge. And in fact, it's in the Cartan algebra. So typically in the SLQC, alpha will be a diagonal matrix of size Q with trace 0. And if you are in SL, so for example in SL2C, alpha, I can always write it as diagonal of A and minus A. In SLQC, it's a sum, it's a diagonal matrix of trace 0. Now when I write J of x e, here x will be a point on sigma 0. E will be an element of the Cartan algebra, or in fact later I will extend it to an element of the Lie algebra. But so, if it is an element of a Cartan algebra, take the example of GLQC, and also J will be a one-form valued. So basically, it will contain a dx. In fact, the true definition, for those who know, is that it is a section of the adjoint bundle of something, tensor the canonical bundle of sigma 0. Okay. If you want, it takes values in the cotangent bundle. Okay. I will come back to that later. Okay, but yes. What I wanted to say is that take, for example, AI equals the diagonal matrix 0, 1 in position I, 0. Okay, this is in the GLQC. This is the basis of the Cartan algebra of GLQC. And it is, so if you take this one, let's call it GI of x. And in fact, let's think, well, I mean, this is just a notation, so basically the diagonal matrix J1 of x, JQ of x, okay, which you can call J of x. Now it's an element of a Cartan algebra. If you take its scalar product with EI, by definition, this is GI of x. Or this is G of x, EI. Okay, I mean, I could, so very often, sorry, these are called vertex, and these are called currents. I think sometimes it's called Sugawara currents, I think because it was first introduced in Sugawara in the 70s. Okay. But the idea is that very often people consider the currents as forming with indices J of x. This is how they are often written in the literature. A set of currents with some index, but when you put them together, it's a vector. In fact, it's a vector in the Cartan algebra. So you prefer to look at it as a diagonal matrix. And extracting the ith coefficient is just taking the scalar product with EI. This is why this notation of putting the EI inside, to say that somehow it's a scalar product, is convenient. Okay. So in fact, J of x is really more in the dual of the Cartan algebra, tensor one forms. Okay. This is just notations, but which I find very convenient. This is not the most standard notation, but this is the notation which are convenient for what we do. Now there are other operators which are stress energy tensor. Tensor T of x, and there will be more generally some W tensors, which I will write Wk of x. But in fact, they can be built from currents. And in fact, T of x is just going to be J of x, J of x. There will be a subtlety when I write that, and let me put a double dot here, which I will explain later. Because, as I told you, I require that my correlation functions, they have poles when 2 points come close to each other. So J of x is a product of 2 J's. So if I wrote J of x1, J of x2, and take x1 going to x2, there is a pole. So basically, J of x1, J of x1 should be infinite.
You mean a singularity, or so pole not in the sense of because they're not analytic, the correlation, right?
Sorry?
There might be monodromy.
The correlations, they are not analytic,
Yeah.
they are modulus square of
Yes. Yeah. Well,
You have a non-integer.
It's okay. It's singular, and this double dot means somehow I extract the non-singular part. Well, what I want to say here is just that knowing the currents, you know the stress energy tensor.
So before you use the bracket to mean a correlation function, but no, the bracket you are writing is in the sense of the
Sorry, I don't put bracket. Sorry, as operators. sorry. So, which means that this should be true inside every bracket.
And the bracket you had also
The
above.
diagonal comma EI.
No, here this is the Lie algebra bracket. This is
Exactly. So it's the other one.
This bracket is the scalar product in the Lie algebra. Okay. We should have used a different notation, but this is very standard for the killing form of the Lie algebra bracket.
Which J are you using? Is there some index I or some E?
Here I'm really, in fact, let me write it this way. Minus 1/2 of sum over I equals 1 to Gi of x, Gi of x.
So this involves a choice of basis.
No, it does not. It's a Casimir. It does not
Yes.
involve a choice of basis. Whatever your choice of basis, it will take the same value. I mean, it's like the trace of a square. Also, in fact, I was right writing the bracket. It was the Lie algebra bracket, but with a minus 1/2. And in general, WK. So indeed, take a diagonal matrix. Take its square, and that's equal to that. Okay. Take its square norms. So this is indeed minus 1/2 of diagonal of J1, J2, scalar product with diagonal of J1, J2. Well, here I use a scalar product, as I said here. in DLQC or SLQC, my scalar product is just the trace of the product of the matrices, and you see it's equal to that. And the trace of the trace is basis independent, so this is why it's basis independent. The WK will play the same role, but instead of being the trace of a square, they are going to be traces of powers, or in fact, in general, the invariants. And in fact, the best way to talk about the WK tensors is to make a generating series for them, which will be the characteristic polynomial. So let me write determinant of, let's call, I don't know, which notations I used. Lambda minus diagonal of j of x1, sorry, j1 of x, j2 of x. So take this determinant, so the characteristic polynomial, expand it as sum of powers of lambda, minus 1 to the k, so k equals 0 to q, lambda to the q minus k, and then the coefficient is what you call wk of x. And with this definition, you realize that T is W2. Because trace is 0, well, first observe that W1 is basically trace of your diagonal matrix. Sorry, is the trace of your diagonal matrix, which is 0. If you think about it, this is just so. The WKs are just the invariants of that matrix. And W2 is just the minus 1 half of the trace of a square. It's just a parameter to put them together in I mean, just to recall that they come from the expansion of a characteristic polynomial. It's it's nothing.
Sorry, this works also for the non-semi-simple type CFT, this W being the T?
Yes.
Okay.
Yeah. Well, in fact, you have to write a determinant, you have to use a representation. Well, in fact, the true definition would be that the WK are the Casimir, so they are generators of the center, of the universal enveloping algebra, at the center of the universal enveloping algebra. You can use any combination of, any combination of WKs is also a good definition of WKs. But if you really want to write this formula, you have to choose a representation rho, and then the WK do depend on which representation you have chosen. But the set of all WKs is independent of representation. The set of all the independent WKs, the algebra of the WKs is independent of representation. And this is called, in fact, the Hitchin map, and I'm going to do that later.
I'm just a bit confused. So should I think of J as Lie algebra valued or Cartan algebra valued?
Cartan algebra valued.
So in fact, this diagonal of J1, JQ is just J.
Yes, if you want. But here, when I write that, in fact, it's more the dual of Cartan, and I make it act on an element of a Cartan to get a number.
So it's an H star valued.
It's an H star times dx. Okay. So basically, now, if you want, we are going to compute such functions, and so we have. So I just introduced the different elements that appear in those functions, in those conformal blocks. You have the vertex operators. They depend on a positional charge. You have the currents. They depend on the position and Cartan element, Cartan algebra element. The stress energy tensors, in fact, they are not on the W, they are not independent from the J. You can reconstruct them if you know the J's. I mean, knowing the currents, you can reconstruct them. Okay, that's just this. So this, you can take this as a definition. And if Q were not 0, you would have an additional term which would be like Q, the derivative d over dx of J or something like that. I'm not going to write it, but that's where you start to have some additional terms.
So in what you wrote for the W case, you do not need to also remove the singularities?
Yes, of course. So let me put a double dot here, but I will show later how to remove singularities. So the idea is that indeed you should take the non-singular part of this.
Just one question. This energy momentum tensor for SL2 usually also involves, apart from the Cartan, the E and F, the generators. So it's not only Cartan, or
Indeed.
but in this case, it's
I wanted to simplify the introduction to start with the Cartan, but I said it that later I will move from Cartan to the general algebra. But in fact, when you want to do this heavy limit expansion, so in the large, in the H bar expansion, somehow the idea is that the Cartan part will be perturbative, and the non-Cartan part will have exponential with negative powers of H bar. It will be the non-perturbative completion. So that's why when you want to make the link to TR, you can start with only the Cartan part.
And you don't have integration over contours so far?
Not yet.
No?
So I'm a bit confused about the notation Q. So I guess the rank of SLQC is Q minus 1. Mm-hmm. So Q here is Q minus 1 or Q? Or this is for GLQC?
Well, no, Q is really the size, is the dimension of the representation. The size of your matrices. So Q is the size of a matrix, and indeed the rank of the algebra of SLQC is Q minus 1. Because only Q minus 1.
So the sum here in your stress energy, it runs
from
rank
Q
or a Q?
Because it depends on your representation. But not all of them are independent, and in particular, W1 is 0. So if you count how many WKs you really have, you have Q minus 1. W0 is 1. So don't count it as a W generator. So in fact, indeed, you have Q minus 1 WK operators because W1 is 0. If you are in GLQ, W1 would not be 0, you would have Q of them.
And W2 is not TX.
W2 is?
Yes, it's
quadratic
in not the 10. Is it different or it's the same?
W2 equal to the stress tensor. The question is if W2 is T of X.
Yes, it is. I wrote it here.
Yes, here.
In fact, this is maybe not the standard normalization. I put this minus 1/2. I'm not sure this is the standard normalization. Probably it's multiplied.
It looks like the standard. Usually, in the standard, in all days, T of X was 1/2.
Yeah. Well, I mean, indeed. So W2 is related to the determinants. And T of X would be the trace of a square, and I'm just using the relation between the trace of a square and the determinant for 2x2 matrices.
So, can I just double check? So your current G of XE, the dependence on E does not assume that it's invariant under conjugation, right? Or it does?
No, it's not.
It's not.
Yeah. But for T, yes, it is.
So this means that when you talk about this representation, you choose a basis.
Yes. Yeah. Yes, when I write this diagonal J1, JQ, and so on, it means I have chosen a basis. But in GLS, in SLQC, there is a kind of canonical basis, which is this one, and I wrote it in that basis.
to write the basis, you need to choose a diagonal part of
Indeed.
the plan. So this
Indeed.
is your choice.
Indeed. So in fact, in a Lie algebra, you don't have a unique Cartan algebra, you have many of them. On the inside, you will even have many bases. So I just made one choice. Indeed, the currents, I mean, the I of x is not, needs the definition of a basis, needs to have chosen a basis, but the operator, I mean, as an element of a dual of a Cartan, this is now intrinsic, this is independent of a basis.
No, there's two kinds of bases we're talking about. Basis in Cartan Lie algebra, it's okay. But in order to define this EFH decomposition, so you need to choose a basis, Cartan Lie algebra in SLN.
Yeah.
And you made this choice.
Yes, we made this choice already. So I choose, so here indeed there is a choice. Indeed, an issue is that this choice might change when you do monodromies. But you will not see that perturbatively.
Does this mean there is no choice?
Sorry?
If it changes, this means there is no choice.
So I'm working locally in a certain region, and then there is a choice. At the moment, I'm just at the level of notations. Okay, so now I will start writing the axioms and starting computing things.
Just to recap, so you will consider CFT obeying all of this?
Sorry?
You will consider CFT obeying all of these
Yes.
constraints? Because this is, for instance, the existence of currents is way more constraining than, not all CFT have currents, right? So this is what you consider, and now you will give us a way to give,
The idea is that topological recursion will give a way to construct that. At the moment, I don't know if these axioms do have a solution. Okay, I'm just setting notations, so I'm just saying that I'm going to look for functions that have certain types of behaviors. And this notation is just to say which type of behaviors it will have, I want to have. And I will write the axioms, so precisely which behavior I want. And now the question is, can you find some functions that do have this behavior? And this is indeed a more tricky question. And I will show you that TR gives some solutions.
Because this question about choosing Cartan or not, your T and W, they do not depend on this choice. They Casimir functions, but you insist that your J
yes, indeed,
is defined by picking some Cartan in the algebra.
Indeed. That's true. And in fact, the true reason to use the J is that somehow they are just there to, in the end, create the T and the W case. I mean, it is Sogawa construction.
But you can say that your J are somehow covariant with respect to conjugation. Then you have
They have a certain kind of covariance.
Yes.
But which I don't want to explain now.
Sure.
Just one last question. If you take the GFF, you can construct stuff. Are there models that topological recursion gives you that are not GFF type?
Yes.
What kind of?
Well, first you can choose any Lie algebra, for example E8, I don't know, you can do the GFF for E8. In fact, I think you can, yes. But in fact you can, well, yes, because then you will be able to take limits, non-local CFTs with this. I think the GFF can also do them, but I think it's still to be developed. Okay. Sorry, I should have not erased that. At the moment, I don't really need to put energy tensors because energy tensors are just obtained by taking some specific values of x, of j's, and summing them together. So let's try to. So, what are the bootstrap axioms? So OPE. what are VOPs? VOPs are the behavior when some variables get close to each other. And typically, imagine you have Z1 on J of X1 U1, and then a product of many others. Okay. So this is a function, locally a function. And indeed, corresponding to what many of you remarked, this will be only locally analytic, and it will be a multi-valued function because indeed, when you there are monodromies, and somehow it's not invariant under conjugation. Okay, what are OPs? OPs are tell you, so it's a requirement, it's a bootstrap axiom telling you what you want as behavior when x1 is close to zeta 1. Yes.
So again, will the bootstrap axiom, will they be translated in property of the spectral curve or property of TR?
More properties of TR.
Okay, so it's not that you can...
So you have to find the good spectral curve.
Okay, but this is not gonna follow from the axiom.
In fact, the axiom will tell you which spectral curve to choose.
Okay, so you can formulate those axioms geometrically and classify...
That's my plan.
And classify all
Yeah.
possible spectral
That's-
curve that give you...
Indeed. I hope to arrive to the spectral curve before the end of the lecture, but I think so it's supposed to come at quarter past, but we started like 5 minutes late.
5 minutes late.
So, but indeed, so the idea is that the bootstrap axiom will tell you which spectral curve to use, and then we shall start using topological recursion and see if we can constrain all the other. So this just means that there should be a simple pole at x1 minus zeta 1. And remember that the current is a one form in X. Okay. The current is a one form in X, and there is a coefficient, and the coefficient will be just the scalar product in the algebra. So it's alpha 1 times the same function but without the j. So this is, and then, so here you see a simple pole, and plus the rest should be holomorphic at x1 equals zeta 1. So this is one of the requirements you want for your conformal blocks.
The dx there is a small one. It's dx1. It's dx1. Just to be sure, so your G is supposed to be current generating the algebra of symmetry? Or,
Yes, they are related to that, yeah. Well, okay. This is not how I define them. For the moment, I just say it's a notation, but yes,
but for instance, you take like UV or whatever, the G, you need to put the stress energy tensor.
Sorry?
So you're assuming that the G is part of your algebra symmetry. Like for instance, for UV, you need to take the T. If you just take the G, then you might not get some well-defined objects.
Indeed. That's what I'm saying. It's a multi-value. You will get multi-valued functions with some monodromy properties, and it's not a function, indeed.
Yeah.
But this is what you want to satisfy. And indeed, when you start taking the square sum like that, you will get now a well-defined function. And this is how we get the spectral curve, by the way. So this is the kind of behaviors we want. But just I'm still in the notation part. The idea is that since this is true for anything you can put there, the notation used by physicists is to write this equation directly at the level of the things inside the bracket. And again, it's just a notation to remember. So the axiom that you want is that this is true for any choice of others here. So in particular, so basically a good way to remember it is to write just this, J of x1 E1. So basically I wrote the same thing without others and without the brackets here, but which means that this should be times the alpha 1. And so this equality, so this relation here just means that this should be true inside any bracket. So I have another OPD, which is what happens when two J's come together. So again, I'm going to write directly in this way, but you should think that you want it to be true inside any bracket.
So when you write alpha 1 E1 in brackets, this is also a scalar product of
the Lie algebra. It's a bit unfortunate that this is the same notation, but this is the standard notation for form in Lie algebra, and the other is the standard notation for correlation functions in physics.
Maybe you can put a little g in the Lie algebra.
I will forget it all the time.
Yeah, you can skip quite
yeah. And in fact, I will less and less use this one. The correlation function brackets, I will less and less use them. I will not use, more or less, I will not use them anymore nearly in the rest of the lecture. Whereas the killing form, I will use it all the time. In fact, here this one is not exactly the killing form. It's proportional to a killing form, but you know that in semi-simple simple algebras, every scalar product must be proportional to a killing form.
So in the reductive case, do you have much more choices?
Yes, you have more choices in the reductive.
And how much does it depend on?
Well, the idea is that you can, in each simple block, you can choose a different normalization. You just make your choice once for all. But for DIQ or SLQ, there is a standard choice. This is this one. You want it to be non-determinate. So you want that. So remember, it contains the dx1, dx2. It must have a double pole. Okay. There is a killing bracket. Well, I call it killing, but just think of it as the. So I will say killing, but in fact I mean the scalar product in the Lie algebra, so which is proportional to killing. Plus.
So it doesn't depend on x.
Sorry?
You want it to this. It doesn't depend on x, or it does.
It doesn't depend on what?
X.
On the argument.
X is the local coordinate, but this E1, E2 are in the they don't depend on X.
No.
Okay, no, it's
Well,
it's still just an
so which means that short distance somehow you've chosen the same basis in the same open set. Okay. Plus, what is the next term? Yes, the next term. So now, let's say for a moment I'm not in the carton. Plus, and now this is the definition of J of x1 E1, J of x2 E2, at x1 equals x2, plus O of x1 minus x2. Okay. If both E1 and E2 are in the carton, this term is absent, because the commutator is 0. But I'm already starting to extrapolate when later I will take E1 and E2 not in the carton, and you want to have this term. But when you are in the carton, E1 and E2 commute, this is 0. So what it means, so remember, again, this should be true inside any conformal block. So you have a double pole. You have possibly a simple pole if you are not in the carton, but in the carton you don't. And this double dot is by definition, somehow it's the limit of that minus the pole. It's the limit at x1 equals x2 of this product minus the double pole. That's the definition. So now you understand what I mean by this double dot, this regularization. You just subtract the pole and take the limit. Okay.
So is it possible that the second order pole is absent?
No.
That they are orthogonal somehow?
Oh, yes, sorry.
And then
yes,
the first order pole is somehow there, and does it have a geometric meaning?
Well, I mean, I want this to work for any E1, E2. I mean, yes, so if you take E1 and E2, this one will be absent.
But there's no geometric meaning because they don't depend on the geometry.
Yes, there is a geometric meaning, but okay, we can debate that later. But at the moment, anyways, I take E1 and E2 in the carton, so this is always 0. On this one, if you take, but remember what it says. It says that if you take different i's, somehow it just means that there is a pole only if it's the same index I. So later in the spectrogram, it means there will be a pole only if you have 2 points in the same sheet, but not in the sheets. And this, which will be a more background problem.
But here we are still assuming that the central charge is, like the Q background charge is 0,
Yes.
right?
Yes.
So if you change the central charge, then you can get 0 if the central charge is 0.
Sorry?
The first term is square can be 0 if the central charge is 0. If I'm not
No, but
mistaken.
it's not 0. Well, very important. So if you want here, I have a 1, and this is related to
Yeah, sure, but there's a way to make it vanish.
Indeed, when you want to compute the central charge, you will need to compute the OPE of 2 T's, not 2 J's. But the fact that you have a 1 here will give you that the central charge will be the rank of the algebra. So it's the 1 here that will give you a after summation of the basis, it will give you the rank of the algebra. So the central charge even is the rank of the algebra, it's Q minus 1 here. I should more or less finish. So now let's write just really the spectral curve. So let's compute the simplest possible. Let's see what the axiom tells us about the simplest possible correction function conformal block. So V alpha 1 Z1, V alpha and Zn. And let's take a T of X. Okay. Let's write it as Q of X. Or, no, I mean, in our relation with Leonia, we choose T of X. And remember, it's a quadratic differential, it contains the dx square, it's locally a quadratic differential. In fact, it's not, when we want to do things globally, it's not exactly a quadratic differential, it's a connection. It transforms not as a quadratic differential, but plus Schwarzian derivative, but in fact, but in the heavy limit, the Schwarzian derivative is multiplied by h bar, and so you don't see it. So in the heavy limit, this will be a quadratic differential. I will come back to that later. But so, what do we want to satisfy? No, it's because I forgot to write the word identities. Word identities will be that T of X must be globally holomorphic. This one must not be multi-value. It must be globally neuromorphic. On sigma 0. So it must not be multi-valued, so it must be locally analytic, but also globally analytic, and with poles. On the poles, the only poles that you can allow are those coming from VOPs. So what does it mean? This function T of x must be globally meromorphic. So in fact, this T of x also depend on alpha 1, z1, and so on. But let me write it T of x because I'm interested only in the x dependence. So remember that this is also a function of the other. It's meromorphic times dx squared. It's locally a quadratic differential, and it must have poles. And what are the poles? The poles of T of x must be the poles of T of x. Sorry, let me divide by v alpha 1 z1, v alpha and zn. Now this is my T of x. Okay. So the poles, so T of x must be meromorphic. And it must behave at the poles dx squared over x minus zeta I squared. Oh, sorry, these are zetas. Times, and if you remember, this should be minus 1/2 of sum over I of alpha EI. Alpha I, sorry, J, alpha A J, okay, on which you recognize as being just the star product alpha I, alpha I. So basically, it's trace of alpha I to a square. So this is a double pole. Then there could also be a simple pole, dx squared. And let me call the coefficient hi. I don't know what it is for the moment. Plus holomorphic. I think it's time. Okay, if you allow me to write just one last equation for an example. So let me just take the example where sigma 0 is CP1, the sphere, and G is just SL2, C. And like alpha I equals diagonal of AI minus AI. Then you see that T of x should just be sum over I equals 1 to n. Dx squared over, so trace of, so minus 1, so let me also write delta I equals minus 1/4 of alpha I. Delta I over x minus zi, so let me put the dx squared in front. So delta I over x minus zi to a square plus hi over x minus zeta I. And this is all what you can have. I mean, basically, the OPE and the word identities tell you that this is all. You cannot have anything else. And so this will be our spectral curve, and I will continue next time from here. So just from these bootstrap axioms, we could get an explicit expression of something.
Thank you, Bertrand.
So I will continue my lecture, and we arrived yesterday at just the hint of what will be the spectral curve that we are looking at. Just let me mention something. Yesterday in the axioms, I forgot. So in the axioms, I forgot one axiom, which is basically the same axioms that Eynard was mentioning. So the gluing axioms, and it's just the same thing. So, which is another axiom that I forgot, and which needs to be addressed at some point if you want to show that what you are doing has some. Also, let me make a general remark. In all these approaches, so the one I'm considering, so with the bootstrap axioms, the approach of Gaussian prefill, the approach that Professor Goncharov is presenting, in all of them, basically you have some axioms that you would like to, basically you would like to introduce an object which you don't even know if it is defined at all or not. And the axioms are like necessary conditions that you want to satisfy, and you have to show that there is something that makes sense out of that. And in my approach, so we have rules. So we have a notation for functions. We would like them to satisfy some conditions. We don't even know if they exist. And we shall build something which has the properties. And to build this thing, we shall use topological recursion. The starting point is a spectral curve. So what we need to start with is a spectral curve. And basically, so far we are just talking about nonsense, but guess what spectral curve we need. When we have a spectral curve, then we have something that does exist, and we can do something with it, and we can do a theory out of it. So what I was presenting yesterday is that imagine that these objects, V alpha 1 of zeta 1, V alpha n zeta n, T of x, V alpha 1 zeta 1, V alpha n zeta n, and I called it T of x, okay? And it's locally, so basically, if it does exist, it has to be a quadratic differential, globally meromorphic on the curve, and whose only poles can be when x is some zeta I. Okay, so does it? So now, so the spectral curve basically will be the data of a quadratic differential. In fact, it's not all. So for the moment, let me focus on the case where sigma 0 is CP1 and G is SL2C, which is the Liouville theory. Before going further, let me also mention another thing. There are several ways of doing topological recursion. One starts with a notion of spectral curve. The other one, which is the one developed by Kontsevich and Soibelman, starts from the data of what's called a quantum area structure. This is equivalent. In principle, these two approaches are equivalent. The other approach makes it easier to deal with Q non-zero. But in fact, they are more or less equivalent. I don't know if Canto is going to talk about that. There is the notion of a Whittaker vector and things like that, but more or less it's the same topological recursion. It's just the data is presented in a different way. I prefer to use spectral curves, but which is simpler if Q equals 0. But all this can be extended to Q non-zero, and for example, we did it with Sylvain Ribaud and we recovered the DOZZ formula to doing orders, and it works. Okay. So now let's focus on this case. In this case, what do you want? You want that T of x, it should behave like dx to the square. It should have poles at all at all the zeta i's with delta I, and delta I will be, so if the alpha i's is diagonal of minus AI, of AI and minus AI, delta I should be 1/2 of trace of alpha I square, which is AI square. In fact, yesterday I put a minus sign. So yesterday I defined the stress energy tensor as minus 1/2 trace of a square. In fact, so yesterday I defined T of x was minus 1/2 trace of J of x square. well, in the algebra notation, this would be J, J. Okay. In fact, I prefer in 2x2 matrices, this is minus, so for 2x2 matrices in SL2C, this is also minus the determinant. Okay. In fact, no, sorry, this is plus the determinant. In fact, let me change a little bit my notation with respect to yesterday. Let me put a plus. Let me put a plus and then a minus here. Otherwise, I will mix the minus signs all the time. Okay. So now T of x, instead of being equal to W2, will be equal to minus W2. But okay, it's just. Otherwise, I think I will mix the minus signs. So T of x must behave like that. Plus, there can also be simple poles. And let's call the coefficients hi. All right. So this is what we would like to have. And what value can take the hi's? They are nearly arbitrary, but there is something which is that, let's say, none of the zeta i's is at infinity. Assume that the zeta i's are different from infinity in CP1, which means that at infinity you would like your quadratic form to be holomorphic, to have no pole at infinity. And for quadratic form, to see that something is analytic at infinity, you should use the variable 1 over x instead of x. And with this, you can show that you would like that this coefficient inside the. Well, basically, you can show that dx has a double pole at infinity when you change x to 1 over x. So dx squared has a pole of degree 4. So basically, you want this to vanish at order 4 at infinity. So basically, a requirement is that all this should behave at 1 over x to the 4 at infinity. This is just the condition that that T of x is regular at infinity. And you see that there is a 1 over x behavior with coefficient sum of hi's, so it has to vanish. So it implies that sum of hi's is 0. You can also check that the next term, the 1 over x squared, is sum of zeta I hi plus delta I should be 0. And sum over I of zeta I squared hi plus 2 zeta I should be 0. So you have three conditions. So this gives you three conditions, which means that the hi's are not independent. Okay, only n minus 3 of them are independent. So n minus 3 of the hi are independent. There is a nice way to find the independent parameters. Instead of writing this way, introduce phi of x equals product from I equals 1 to n of x minus zeta I. We can rewrite for T of x as follows. 1 over phi of x sum over I equals 1 to n delta I pi prime of zeta I over x minus zeta I plus sum from k equals 0 to n minus 3, no, n minus 4, h tilde k, zeta k, sorry, xk, dx squared. So the h tilde k is now, there are n minus 3, and they are now independent. You can check that. Let me do more explicitly the case n equals 3. In the case n equals 3, T of x is something with product from I equals 1 to 3 of x minus zeta I to the square, dx square. And in the numerator, so the denominator has degree 6. We want it to behave as O of 1 over x4 at infinity, so the numerator must be a polynomial of degree 2. Let me write it in this way, c times x minus a, x minus b. Just a generic polynomial of degree 2. This is just to show you, yeah. Okay. So typically this is what you get. So now, remember the motivation for doing that, which was that we wanted locally that t of x would be the 1/2 of a trace of j of x squared, while j of x would be, so if it would exist, would be a diagonal matrix. Let's call it j1 of x, on minus j1 of x. You can write j2 of x. And if all this is going to make sense, in some sense, you would like the eigenvalues, t of x. Well, let's compute the characteristic polynomial, y minus j of x. It would be equal to y squared minus y trace of j, which is 0, plus determinant of j, which is minus t. So it would be y squared minus t of x. And it vanishes when y is j1 or j2. Okay. So this is just to say that the spectral curve that we want to consider now is the curve of equation y squared equals t of x. So this will be our spectral curve. So on t of x must be, well, either this expression or this expression or this expression, I mean any of these, but this is what we want to look at. So now we have an algebraic equation, an algebraic curve, and we just now want to study the geometry of the first question, which we will use now as our starting point. So given some delta i's and zeta i's, we have such a curve. Now it's an object that exists, and we are going to start from it.
So to get the spectral curve, you looked for zeros of a characteristic polynomial.
Yeah.
Could you explain a bit more why?
For the moment, it's purely heuristic. It's again that if the current would make sense, it would be the eigenvalues. Because, or let me say it in another way, you want to find a diagonal matrix such that 1/2 of a trace of its square is given by t. And so you want to find a diagonal matrix whose trace is 0, and the trace of its square is t. And basically you have to solve this equation.
So can you explain again why you get the little t of x? I mean, so the determinant of j, that was capital T?
Take the trace of that matrix to the square. The trace of that matrix to the square, by definition, is t of x.
Or capital T.
Yes, but small t is its expectation value, and so basically heuristically, this is what you want to get in at least in some limit. This is just, so again, this is just a motivation for which spectral curve to use.
Okay.
This is not a derivation because this does not exist at the moment.
Small t of x was a quadratic differential here.
Yeah.
Here it's a function.
No, y is a one
Y
form.
is a one form.
Y is a one. Remember, j is a one form value, so y is a one form, and basically you're looking for one form to the square equals t. I mean, locally a one form. It cannot be globally a one form, or it will be a one form on the cover. And indeed, I want to study that cover. So let's look at this. In fact, yes, let's write y equals y tilde times dx. If you're on CP1, you can do that. If you're not on CP1, dx does not make sense.
Sorry, so how can you find this one form? How do you always know that t has such a one form? Because t is a quadratic.
You can always take the square root of a quadratic differential. It is multi-valued, and this is how you define it.
Okay.
This is the definition. So y is a multi-valued
okay.
form, or if it's a one form in a cover. And this is what I want to describe now. Which cover? So let me write it y tilde dx. And by definition, in this example, y tilde to the square equals c x minus a x minus b over product of I equals 1 to 3 of x minus b to the square. And this is an algebraic curve. You can plot it, okay. But you see that when you take the square root, well, here it's a perfect square, so there is no problem. But here there are 2 points at which you will have something non-analytic. These are the branch points. And a way to think about that curve is you have your 3 points, zeta 1, zeta 2, zeta 3. You have your points A, B. And because you are because you are taking a square root, there are 2 determinations of a square root, so you will get a 2-sheeted cover of a plane. So let me take another copy. And you must glue them. You should glue them along a cut, along the cut AB. Gluing is more like opening a slot. It's like a cylinder. And you can see that this curve, this plane is in fact CP1, it's the sphere. Let's close it at infinity. This one is also a sphere, you can close it at infinity. And see that this is a curve of genus 0. And in fact, whenever you take the square root of a polynomial of degree 2, you get a genus 0 curve. If you would consider n not equal to 3, if you take n larger than 3, by the way, you notice that for n strictly less than 3, this has no solution. It's similar to what I was mentioning, you need at least n equals 3. So for n strictly larger than 3, you need to take the square root of that polynomial. Again, you get an equation y tilde squared equals product from I equals 1 to n x minus zeta I to the square, which is of degree 2n. And so the numerator must be a polynomial of degree at most, let's call it p2n minus 4 of x. It must be a polynomial of degree at most 2n minus 4, which means that you have 2n minus 4 branch points. So you have n minus 2 cuts, and which means it's a curve of genus n minus 3. So you will get something with something like that. And the genus would be n minus 3. Okay. Yes. Let me now look at a slightly more general situation. Let's now take G equals SL QC with a Q larger than 2. Q larger than 2. Again, you would like, so the heuristic is that you would like to find something like a diagonal of J1, JQ with such that S of J equals 0 because you are in SLQC. And you would like that the determinant of y minus j would be, and this is how I define the WK polynomials, operators, k equals 0 to q, minus 1 to k, y q minus k, and the coefficient is made of the invariance of j, which I define inside the brackets with the WK operators. The WKs okay, so let me again use another notation. We can put them WK hats, where WK hats would be, if it would make sense, the V1, V alpha 1, zeta 1, V alpha n, zeta n, the WK of x divided by V alpha 1, V alpha n. Okay, so take the expectation value of that. Due to the word identities of the OPDs, you know that it should be a globally meromorphic differential of order k. And take this expectation value and define this spectral curve. There is a trick to find the genus of that spectral curve. I will show you. It's nice. It's a nice trick. So now you want to solve so we want to solve you want to find a certain polynomial p of xy equals 0, which will be sum over k equals 0 to q, minus 1 to the k, y q minus k, w hat k of x, where w hat k of x is a case order meromorphic form, which has poles with poles at zeta i's of a certain degree, at most k, and with some coefficients that will depend on the invariance of your alpha i's. Trace of alpha I squared, trace of alpha I cube, and so on. So, and again, only some coefficients of that equation are constrained by the value of the charges, and some coefficients are not. Exactly like here, we had these coefficients that are constrained, or these coefficients are constrained by the behavior we want at the poles. And this one was not determined by, it was free, except these 3 conditions. It was free, so you had n minus 3 parameters. Here, or in this version, these are totally free coefficients. They are not implied by the OP. So here you have the same thing. There are certain coefficients of P that are implied by the OP, and certain that are not. And the question is how many are implied by VOPs, how many are free, or if you want, what is the moduli space of possible P of x. I give you a hint. The dimension of the moduli space is going to be the genus of a curve, which is standard in teaching systems. But okay. But now what is the genus of that curve? So the genus, so now if you would take y to be some solution of that equation, if y would be some solution of that equation, well, this equation is of degree q, so it will be a q So you will have Q sheets to glue together. And in each sheet, Y will have only simple poles at the zeta i's. So the zeta i's, for example, zeta 1, so these are 3 copies of zeta 1. Well, let me write the charges alpha I to be alpha I1, alpha I2, alpha IQ. So diagonal. In fact, the OPEs precisely tell you that a Y solution of that equation should behave in some sheet as in the sheet J as alpha ij over x minus zeta I plus holomorphic. And so here you will have a residue alpha I1, here a residue alpha I2, here a residue alpha I3, and so on. And you have a certain number of branch points on cuts that can do, I don't know, many things. Okay. What I want to show you now is, can we find the topology of that spectral curve just from knowing these behaviors?
Bertrand, did you say the space of spectral curve is G-dimensional? The dimension of the space is the same as the number of genus?
Yes.
But here, for example, you have many choices to pick WK, right? At least rank, so it's related to the number of rank, no? So,
what do you mean? Sorry.
So if I want to fix P of X and Y,
yes.
I, in principle, or if I want to have some algebraic curve between X and Y, I can, in that form, I can choose WK.
Yeah, this is the, this is more or less the same thing I'm saying, is the number of WKs you can choose, the dimension of the space is going to...
That's related to the rank of the W algebra. But it's related to the rank of W algebra. But it's not, depending on how I choose, then the genus is a bit different.
Well, it's okay. I will come to a Hitchin system later on. Here, so the projection to the base of the system, and the base is G-dimensional and the fiber is G-dimensionalized.
Okay, so there's probably some extra assumption to say that.
Well, at the moment, all what I require is that in different branches, the poles are simple poles with this type of behaviors.
Ah, sorry, okay, so yes, okay. Yes.
This is equivalent to...
Okay, no, then I think, yeah, okay. Yeah.
So you look for all curves of degree Q such that the only singularities are simple poles with these residues in all possible ways. In fact, in the end, all what you can choose are the periods around A cycles. And there are G of them. This is what I'm going to do now. Okay. Let me tell you a mnemotechnic trick I'm not going to prove. I'm just going to tell you a trick recover the genus of that curve. So imagine you have SLQC, you have endpoints, and you have endpoints, and you have sigma 0 CP1. So take your endpoints in the plane. So here n equals 5. Draw a graph, a trivalent graph. This is often called a channel in CFT, a type of channel. So let's label this point zeta 1, 2, 3, 4, 5. Okay. And let me do something. Let me take Q copies of the same graph. Slightly shifted. So I take Q of them. So Q copies. You get a graph. this graph has loops. And basically, the number of loops is going to be homogeneous. And also, if you want to understand the topology of your spectral curve, you're going to thicken the lines of the graph to tubes. I mean, just let's thicken this graph. Let me do it. Okay, and here you have one hole here, you have two holes there, one hole there, two holes there, and one hole there. These are the small 3 holes and the 4 big holes. Okay, so this is just a thickening of that graph, and this is your curve. There is a formula for the genus.
Did you forget the last 2 holes? Or
Sorry?
Sections are really
forget the last 2 holes to the right?
Which?
The holes are, how do you see where the holes are?
This one is this one, this one is this
I
one.
can't see the
One
other.
cannot see the.
We need to see both fingers.
Okay, sorry. This one is this one. This
Okay,
one
yeah.
is this one.
It's all right.
This one is this one. In fact, you see there are holes associated to edges and holes associated to vertices. And let me give you a formula for the genus. The genus of the curve will be n minus 3, which is the number of edges, times q minus 1, plus n minus 2 times q minus 1, q minus 2 over 2. You should verify this formula. You can check that for q equals 2, you get n minus 3, which is what I said before. Okay. And in fact, you can even generalize this formula a little bit further. Let me. Write it this way. In fact, I will need that later. But imagine that your curve is not. Imagine that sigma 0 has a genus G0. Okay. Replace G by some Lie group, by some, well, say, I think semi-simple, probably you need. Any semi-simple algebra at the moment. By the way, the construction I'm presenting here is really for ADE, because there was the question yesterday. In fact, now we have found a way with Raphael and my student Soufiane to extend it to also BCFGs, but it's more, there are more, I'm not going to go over that today. So then the genus would be n minus n plus 3 G0 minus 3, which is the number of edges of the graph, times time rank G. Well, okay. Let me talk about the Lie algebra. Plus n plus 2G0 minus 2, which is the Eynard characteristic, so which is also the number of vertices, times G minus 3 rank G over 2. So this is the general formula. For if sigma 0 is the Riemann sphere, this comes back to that one. But this is the formula in general. Okay, I'm not going to prove it, just believe me. But it's a simple algebraic computations. So in the end, we have a curve like that. In the end, we have a curve like that, which has bad genius. And we have a projection from that curve to the base to sigma 0. Okay. In this projection, any of those poles here are sent to the same zeta 5 here, for example. These three are sent to zeta 1, and so on. Okay. And this is a 3. Well, this is a Q to 1 projection. So this curve is a curve of degree Q of base. You have a certain number of branch points, which are the extremities of these things. Okay. Yes, yes, on Y is a one form valued in the cover, which means that when you project it, it becomes a one form multi-valued, like the square roots. Now you have non-contractible cycles on that curve, and you will have periods. And the number of independent periods is the number of independent cycles is 2 times the limit. So let's make a choice of what's called a synthetic basis of cycles, which is also called the Torelli marking of the curve. So let's make some choices. Okay. Let's take this cycle. This cycle. In fact, I'm not going to take this one because somehow this one is minus the sum of the two others. Also here. Okay. Here you have more choices, like we could take this one. Okay. And let's take B cycles. Okay, you have some arbitrariness in how you choose your cycles. Sorry, I should have taken, the right one here. And now let's take some would be like that. And so on. And here, take that one. Here, take that one. That one. And that one. Okay. But in the end, you have 2G cycles. And this is a choice. And let's call them A1, AG, B1, BG. Okay. This is totally arbitrary. I will just require that AI inter AJ, they don't intersect. BI themselves don't intersect. And AI DJ is delta IJ. This is called the symplectic basis of cycles. This is a totally arbitrary choice. In fact, given your graph, it's very tempting to take the A cycles corresponding to edges. For vertices, it's less canonical. Or you could choose the A cycles to be those cycles, I mean, to correspond to these cycles, but then the B cycles are arbitrary. So there is not a unique choice of that, but let's make some choices. In fact, the A cycles together, they make a Lagrangian with respect to the symplectic structure of the intersection form. The B cycles make a Lagrangian, and together these are called polarizations.
Sorry, I'm confused about this. The B cycle, the yellow one. That why you don't have just only for the origins? You have to go to.
Sorry. Maybe I made it wrong, but the A cycles are in yellow and the B cycles are in red. The A cycles are in red and the B cycles are in yellow in this picture. And I hope they satisfy what I said. Always I made a mistake, but I think they satisfy what I said. So there is no A cycle, so all the A cycles don't intersect each other. The B cycles don't intersect each other, and the A on each B cycle intersects only one A cycle.
In the rank 1, is the surface always hyperelliptic?
Yes. Yes. In SL2C,
yes.
which is it's always rank 1 is always SL2C. Okay. But yes, it's hyperelliptic. Okay. So then you see. I told you that the number of HIs that are independent, that you can choose arbitrarily, is equal to the genus. And for the general case, you have to believe me also, but the number of independent parameters of your curve is equal to the genus. And one way to parameterize them is to take half the cycles, let's say the A cycles, and define the periods which I call epsilon I equals eta I, 1 over 2 pi I, integral over the AI cycle of Y. Y is a one form, you can integrate it on the cycle, you get a number. And you divide by pi. And so you have, for I equals 1 to G. You have the same number of eta I's, as the number of independent HIs. Or basically, the eta I's can be used to locally parameterize your spectral curve. The moduli space of possible spectral curves, these are local coordinates in the moduli space of spectral curves. I forgot to mention, since you have poles, you have also other non-contractible cycles, which I will also put in red. You have non-contractible cycles around the punctures. And you could do the same, compute the integral of y around those cycles divided by 2 pi I. And since you're surrounding a simple pole, you are just computing the residue on the periods are the alpha ij's. So the periods, so let me draw so here, for example, this is alpha 2, 1, alpha 2, 2, alpha 2, 3. The sum of them has to be 0. Here, this is eta. Okay, let's call it, this one was eta 1, eta 2, and so on, eta 3, eta 4, eta 5, and as you like, eta 6, and so on. Okay. And here you would have alpha 3, 3, alpha 3, 2, alpha 3, 1, okay, and so on. For each such periods. In some sense, if you would imagine you are doing gluing rules, if you would cut your surface here, then this would correspond to boundaries and they would be very similar to the charges. And in fact, they are called the internal charges, these periods. Let's call them the internal charges. There are some associated to the edges of the graph. You could define here another eta for that cycle, but it would be minus the sum of the two others. Because the projection is such that every time you have, I mean, the sum of the three copies must be 0. So in fact, here, the vector made by these three etas is, I mean, if you take the diagonal matrix made of those three etas, it is again in your Cartan algebra. And it's like a charge. So that's why you can call it a charge. It's an internal charge. For the charges internal to the vertices, the interpretation is a bit more tricky. But basically, we have also internal charges in the vertices. Right? So what else to say about that spectral curve? What else? What did I want to say about the spectral curve? So the bottom line of all that is that heuristic led us to consider a certain spectral curve on a certain space of spectral curves. So from the heuristics, we are led to consider a space, a moduli space of spectral curves, which are of the type, let me write that P of x1 equals 0, such that so it's a degree Q cover, and such that locally at puncture, so the only singularities of Y are simple pole with residues being the alpha ijs. Okay, and the moduli space of spectral curves, let me call it M, and the dimension of M is G. You can either parameterize choice of M by the coefficients of P, and in particular the coefficients of P that are not dictated by the charges, and you can call these Hamiltonians. So the coefficients of P that are not given by the charges, you can call them Hamiltonians. And the but otherwise, there is a local coordinate. Local coordinates are the periods theta 1, theta 3. And let's recall that. And remember, I wanted to label my conformal blocks by some, I mean, the basis of conformal blocks by some index, and the index will be somehow eta. Right. So this moduli space is not empty; it contains many curves, and it makes sense now. So now, for the first time in this talk, we have something that is well defined. We have a space of spectral curves, because any of these objects for the moment was not defined. It was just hoped to be defined.
So if I understand correctly, we got to this construction heuristically, and now we're going to check that it satisfies.
Exactly. So indeed. So now we start from this moduli space, and we are going to use topological recursion on it to build things that now make sense, and we hope that they satisfy all the axioms. So it's a bit similar to the other approaches. You start, so you have something you would like to exist, but you don't know how to define it, like the integral or this mysterious vector that you were talking about. And you start from something that you know, like combinatorics of graphs. So here it's a similar approach. You start from something that you don't know if it exists, you see what it would imply, and then you have something that exists, and you are going to build something else.
The branching point in this surface. How to see the branching point in this surface?
Well, you can. There is the Riemann-Hurwitz formula which tells you the number of branch points given the genus. I mean, you can find the number of branch points. Let me not care about that. I mean, you can compute it. It's just an exercise. We don't have to worry. No, in fact, so we will have to worry about them. And in fact, this is my next point.
But can you see them from the graph or the?
Not really. I mean, the graph is just a picture to remember the global topology structure. It doesn't tell you what is the projection. You don't really see the projection from the graph.
And they don't have physical meaning? These branch points?
Sorry?
The branch points, do they have some physical? I was thinking maybe they have to do with some rules in the Bethe
In fact, no, this is not how I see them. But you could investigate but this is not what they will be used for. They will be used for topological recursion. Topological recursion is a recursive procedure which consists in computing residues at branch points.
So concerning the choice of two cycles, if I take a different choice in the CFT, is this a different channel? Or
Yes.
So you can go all channel?
Yes. The idea is that in the end, somehow the crossing symmetry axiom is that what you get in the end should be independent of your choice of channel. So if your construction is going to make sense, the final thing should be independent of this choice. But for the moment, let's make one choice. It's just to use local coordinates. In fact, because also topological recursion needs some keys. Okay. Yes. There is. Yeah. In fact, this moduli space is very much used in the framework of Hitchin systems, and I would just say a few words about that. Hitchin systems. So let's consider the moduli space of X field. The moduli space of X field is the moduli space of phi of x, which so basically it's I could write it as so it's the moduli space of the algebra valued one forms. The algebra valued one form. In fact, it's well, I think the correct notation is H0 of sigma 0 into the adjoint bundle of so you take a G bundle, tensor K sigma 0, and with poles at the zetas. So where P is a G bundle. Is a bundle. This fiber is the Lie group G. This is one way to formulate that. But what does it mean? It means that any element of that space, well, in principle, the moduli space of X fields is modulo the gauge group. But let's take a representant in that space. So it means it is a so phi of x should be a one form valued, and in the Lie algebra. So basically, it's a matrix times dx. So in the SLN case, it's a Q. Sorry, in the SLQ, it's a Q by Q trace 0 matrix times dx. So think of which has only simple poles at the zeta i's, and whose residues should be fixed. Also consider phi of x as. So take again sigma 0 equals CP1, P the trivial bundle, P equals G cross sigma 0 to sigma 0. and take G equals SLQC, then phi of x to take that form, sum over I equals 1 to n, phi I is the x over x minus zi, where phi I belongs to your Lie algebra. The fact that there is no pole at infinity means that sum over I, phi I should be 0, meaning that there is no zeta I at infinity. In SLQC, you want that trace of phi I equals 0. And the OPEs tell you that the eigenvalues of phi I must be alpha I. So how many such matrices? So basically, if I give you the zeta i's and the alpha i's, how many such matrices can you find? What is the dimension of that space? What is the dimension of that space? What is so what is the dimension of that space? And I tell you it's 2G. And one way is that this space, you can project it, and it's called the Hitchin map, by taking all the invariants of phi. So you take trace of phi, well, which is 0, by the way, trace of phi square, trace of phi cube, and so on, trace of phi to the cube. And this belongs, so the space to which, so this is a quadratic differential, a cubic differential, and so on. The space to which it belongs is called the Hitchin base. But if you think about it, these are the same as the coefficients of my polynomial P of xy. So in fact, under the Hitchin map, a Higgs field gets projected to the data of a spectral curve. And the dimension of a space of spectral curves we have already seen. So the dimension of this space, with all these constraints, is the genus G. And what Hitchin showed is that the dimension of a fiber is also G. And so here, in the base, local coordinates can be the periods. We are also called the conserved quantities in the setting of Hamiltonian systems. And the coordinates in the fibers are called the angle variables. So, or if you want, these are called the action variables. And coordinates in the fiber are called the action angle variables. There is a whole literature on that. It's the realm of Hamiltonian systems, Hitchin systems, and all that. You can read about that. I'm not going to elaborate. It is just that in the end, the moduli space we are considering is really this moduli space of Higgs fields.
Is there any property that you have in the Higgs field structure that you don't have in that?
Not really. I mean, it's almost equivalent from this. Well, the idea is that here, somehow, the spectral curve tells you what are the eigenvalues of phi. And here, if you really want to reconstruct phi, you also need the eigenvectors. Eigenvectors are parameterized by what's called the divisor, which is this angle variables. Point in the Jacobian. In fact, the fiber is the Jacobian of the curve. So knowing the eigenvalues, you want to reconstruct the eigenvectors, and then you know this.
Is there any counterpart example that you can have some well-defined Higgs field example that you are not able to write a spectral curve?
No, it's really equivalent.
So I think here we are still at the central charge C called the rank of -1 perhaps.
Yes.
And if you were to take a generic background charge?
Okay, that's where it's simpler in that case to start using the formalism of Kontsevich-Seibelman or to introduce a notion which we call non-commutative curve. And you start to have x and y which don't commute and whose commutator will be q, by the way. And this is what we did with Eynard and Sylvain. So it works, but it's much more complicated to explain in a 1 hour talk.
On this side, would that be related to non-abelian Hodge correspondence?
It is related, but it's not exactly the same thing. Non-abelian Hodge would be a kind of different way to view things. But yes, there are deep relationship to non-linear corresponds, but this is not totally parallel to this direction I'm going. Okay.
There is terminology that makes you think of analytical mechanics. When you say action angle, variable.
I mean, this is mostly what Hitchin did in this setting. I mean, this is a Hitchin theory on. It fits with what was known before from Uville and all that. Okay. So basically, all what I wanted to say, I'm not going to elaborate on Hitchin systems and all that. All what I wanted to say is that this is the good data to start with.
Just to come back to the question, so if you want to go away from this particular central charge, your spectral curve is no longer a curve, it's an operator. And what about the recursion? You still have Bergman kernel.
Yes.
And,
yes.
Can you give a
it's not fully finished or published, but we can discuss that at some point. The SL2 case is more or less what we have done with Sonia, but the SL2 is not yet published.
What was the question? It's very hard to hear.
Yeah. So she says, basically, so if you replace the spectral curve by something by non-commutative spectral curve, can you run the topological recursion on it? And the answer is yes, and this is what we have started developing with Fioria, at least for Q equals 2. But in fact, that can be extended to a more general case, which is not yet fully published. Okay. But yes.
Commutative mean quantization or
yes, it's a kind of quantization where the commutator of y and x will be q. Okay.
What then, if in the standard topological recursion you have the Bergman kernel, right? What would that become?
Okay, we can talk about
once again, so you should repeat the question because it's very hard.
What is the Bergman kernel? But by the way, I'm going to talk about the Bergman kernel in the q equals 0 case now. So in fact, to run topological recursion, you don't need only a spectral curve, you need something more, you need some other object on the spectral curve, which is called the Bergman kernel. So now we have a curve, we have this spectral curve, which has this topology and so on, and the question is, does there exist?
So for S2 is sigma 1.
Sigma.
Yes, exactly. Capital Q plus 0.
So what does it mean? It means that B depends on two variables on the curve. So you're going to need a B of Z1, Z2, where Z1 and Z2 are points on the curve, not on the base. They are points on the curve. Okay, they have projection to a base, but imagine 2 points with the same projection. They are 2 different points. Which is locally a 1 tensor 1 form. So it's maybe DZ1, DZ2. This means that there is a double pole when Z1 equals Z2. 1 over Z1 minus Z2 to the square plus holomorphic. And the 1 here means the residue, the biresidue 1. So does there exist a differential form? Does there exist a differential form which in the local coordinates behave like that? And the answer is yes. You can use Riemann-Roch theorem to see what is the dimension of that space. And I think this is G squared over 2, GG minus GG plus 1 over 2. So the dimension of that space, so it's an affine space because of this one, is G plus 1 over 2.
Do you ask it to be symmetric?
Yes. That's why there is over 2. So yes, sorry. Symmetry. Okay. So there exist such objects. There are plenty. One way is to take the green function on the Riemann surface and take the second differential, the differential with respect to the two parameters. It will give you such an object, which in fact will be in that case called the Schiffer kernel, and it does work.
Schiffer.
Yeah, Schiffer kernel. So, in fact, there is a way. So, first, let me take the case where sigma, where g equals 0. When g equals 0, this b is unique. So, on the Riemann sphere, there is a canonical coordinate z, which is the complex variable. And if you take dz1, just dz1, dz2, z1 and z2 to the square, on the sphere, it makes sense because now z is a global coordinate. You can check that this object is invariant under Möbius transformations of the sphere. It's unique. It's the unique one you can make on the sphere. If g equals 1 and you parameterize your curve as a torus, 0, 1, tau, and z is the coordinate, so z is z plus 1 is z plus tau. Okay? You can construct some b. You could take b of z1, z2 to be, so you want something that has a double pole, one z1 equals z2, and an easy thing is to take the Weierstrass function z1 minus z2 tau. Okay, this is the Weierstrass function. By definition, there's a double pole at the origin with b1. Plus, you can add any constant to it. And this constant corresponds to the dimension 1 of the space. On any complex constant, so it's, you have a dimension 1 of spaces. There is something special that happens if you take C equals the G2 Eisenstein series. When C equals the G2 Eisenstein series, which is also equal to, I think, pi square over 3 times the E2 Eisenstein series. I don't know if you can read that. If you choose this specific value of C, then P is normalized on the P cycles. Write it here. So remember that we had chosen some A1, AG, and B1, BG cycles. Symplectic basis. The thing is that there is a unique B in that space, which is such, so there is a unique B such that for every Z2, the integral when Z1 belongs to the A cycle of B of Z1, Z2 is 0, so for every Z2. So there is so this B is unique, and this is the one we use to call the Berman kernel. In fact, there is a famous Bergman kernel in operator theory. This is another one, but which was also, in fact, introduced by Bergman. So it makes sense. I mean, Bergman and Schiffer. So, in fact, this kernel was much studied by Bergman and Schiffer, and there is, in fact, a book about that from Bergman and Schiffer. So I think it deserves to be called the Bergman kernel, but the reason why it was called the Bergman kernel, I think, is somehow a mistake of Kokotov and Brodkin. But let's continue. In fact, they even wrote it the Bergman kernel. But let's continue with that notation. But nevertheless, it's meaningful to call it the Bergman kernel. In fact, for the first time, it was not introduced really by Bergman, it was introduced by Riemann. And Riemann called it the second kind, the fundamental second kind differential. So it's also the fundamental second kind bidifferential in Riemann. This is much shorter to say that. Okay. So please let me call you the Bergman kernel. polynomial, although it's not exactly the same one as in operator theory, but the two are very closely related. This is why Bertrand studied this, because it's related to the green function. So in fact, when you choose that C is the second Eisenstein series, then this is the Bertrand kernel. Okay. So now, what do we have? We have a spectral curve. So we pick an element in our moduli space, which is a spectral curve, which we can parameterize by the periods. To that spectral curve, we associate a Bertrand kernel. And the data of the spectral curve on what I will recall the spectral curve. And what we need in the construction we made with Nicolas Rentin nearly 20 years ago is the data of this P of xy equals 0 together with the choice of B. In our paper in 2007, we imposed that B would be the Bertrand kernel, but what we have understood later is that this is not necessary at all. You can take any C that would work the same, and you have very similar properties.
By the way, in your explanation for elliptic curve, A and B cycles are 0, 1, and...
Yes, sorry, this is the A cycle. This is the A cycle, and this is the B cycle. This is standard. Right. So it's almost time to stop. So indeed, this spectral curve. So let me say a few words indeed about the branch points. The branch points, by definition, are where two sheets are equal. So typically, if you have so above a point here, x, you have several values. Well, okay, let me write it this way. Above a point x, in the fiber, you have several values, y1 of x, y2 of x, y3 of x. They are defined only locally. But a branch point is precisely when some yi of x equals yj of x. If you put them together in a diagonal matrix, a branch point is when you have yy minus yj equals 0, which is the root alpha ij applied to y of x. So a branch point is a point where there is a root that annihilates your Cartan vector. So x equals a is a branch point if there is a root. Let's call it beta because I used alpha for the charges. There is a root beta such that beta of y of x equals 0. X equals so I should not choose. No, sorry. Let me call it B because again I used A for the eigenvalues. So y of B equals 0. So B. So here x equals B is a point where at least two eigenvalues come together. And we can use the notation, and so to each branch point will be associated a root. And also, by the way, minus beta will also annihilate it. So in fact, a pair of roots, beta and minus beta. And for higher degeneracies, you can have in fact several roots. You get the same point, but in the generic case, you have only one root. This is the starting point to use topological recursion. I'm going to stop here. So the next time I will say, so given this data, we can construct some formal series in H bar, which will be solutions of the OPEs, of round identities. Question, are they solutions of the other axioms, like crossing symmetry, gluing, and all that? The fact is that when you get formal series, this formal series will be divergent series. On divergent series, to make sense of divergent series, it's good if they are resurgent. And also, you know that if they are resurgent, you need resurgent theory. When you get something out of divergent series, you need to complete the divergent series with what's called trans series. And to really understand crossing symmetry or gluing axioms and all that, you need trans series. Basically, you need not only the perturbative expansion, you also need non-perturbative part on how trans series change when you move in the parameter space, and it moves with wall crossing formula. And there is a whole story of that. But the idea is that in the end, you get a conclusion of something that obeys all the end. Thank you. In fact, let me do a small recap of what we did, of what I did so far. From physics, we would like to compute, so let me do a small recap. So from physics, heuristics, we would like to compute, define, whatever, some amplitude, which we can write V alpha 1 of Z1 of theta 1, V alpha n, theta n, and with currents. In fact, the true amplitudes we are interested in are not insertions of currents, they are insertions of free energy tensors or things like that. But currents are just an intermediate step to define the amplitude with free energy tensors, and the advantage is that it's easier with currents. X1, E1, J of Xn, En. Okay. We would like to define such objects, whatever they are, and by taking traces of squares of J and so on, we shall get the stress energy tensor. So if we are able to define these, we shall also be able to define the others. And for that, we use axioms, so bootstrap axioms. They are necessary conditions. These are necessary conditions. In particular, in the bootstrap axioms, there are word identities that I will mostly focus on, but there is also gluing, crossing symmetry, and a few other things like modularity, which I didn't speak about, but that should in fact be a consequence. So I will mostly focus on OP and word because they are local properties, whereas these involve more global properties. So let's start by just using the local properties. So which is OP is the behavior at small distance. Word is a condition on invariance. To make sense of that, so now the goal is to find something that defines all the axioms. To construct something that satisfies all the axioms. And for that, I will start with a spectral curve, but before that, let me say that we shall work perturbatively. Which means that we shall rescale charges alpha I to 1 over h bar alpha I, and define everything as formal series in h bar. As we shall see, these series are divergent, which means when you have divergent series, it's not really formal. It's not really power series. It's not asymptotic. Divergent asymptotic series. They need to have some non-complex. This uses resurgence. And it means that you need to define some other objects that are, from divergent series, you will be able to define other series, which are in fact called trans series, and it's only after you introduce all the trans series that you can hope to satisfy the global properties. Okay, but at the moment at the moment my goal is really to define everything as formal series in H bar. Let me give a name to that conformal block. And remember that it may depend on some parameter eta, which parameterizes the conformal blocks. Let me write it really as a function of x1, e1, xn, en. And all the other parameters, the alpha i's and theta i's, let me put them here. And also the etas. In fact, because what I will be interested in is mostly how they depend on x1, x2, and so on. So basically, I will keep the alpha i's and theta I fixed, the eta fixed, and let me put the n here on the hat. The idea is that we are going to define, write the wn's hat as some over, let's say k, h bar to the k, wn hat k, okay, and the wn hat k are the invariance of topological recursion from a spectral curve. So, topological recursion is a procedure that if I give you a spectral curve, it gives you a sequence of objects. And basically, this is what we are going to use.
I have a question. Is this the disconnected expectation value or the connected?
Yeah, disconnected, that's why I put a hat. Okay. Disconnected or not normalized. I will go to the normalized and connected ones in a minute.
Because what topological recursion is computing are the connected ones.
Yeah, but just by mixing them, you can also get the non-connected.
Yeah, sure.
Just by multiplying and adding. So that's why I write it not WGN, but WNK. Okay, and so the starting point, so basically what we are going to define are really these quantities. And for that, we shall use a spectral curve. So we take a spectral curve. We apply TR, and we get some Wn hat k associated to that spectral curve. This is the procedure we want to follow. And the claim is that when we do that, we get something that obeys the OPs, word identities, and if we use the non-perturbative completion, hopefully we also solve all the other axioms. So now I remind you that our spectral curve, we were considering a moduli space of spectral curves, let me call it M, which was the set of all spectral curves that can be written in the form P of x, y equals 0, so a polynomial equation, such that the one form y, so what I write y is, if the base were CP1, let me write it this way, and because y is a one form, y tilde is when you divide by dx, which you can do only if you're on CP1, otherwise it doesn't really exist. But so y has any simple pose. Above the theta i's at theta I place, which are the pre-images of theta I in the different sheets, with residue alpha ij. So where alpha I, let me write alpha I equals the diagonal of alpha I1, alpha I. Okay, and so and also we make a choice of let me write polarization, which means a choice of A cycles, A1, AG. So in fact the span, which is Lagrangian in the space in the H1, the curve. When we have a polarization, there is an associated Bergman kernel, and also once we have a polarization, we can define some local coordinates that are the periods, eta I equals 1 over 2 pi I, integral over AI of y, which are the periods. And these are local coordinates in this and they depend on the choice of polarization, so they cannot be globally defined. Okay, so this is our spectral curve. Let me make a few small remarks. Here we focus on Y having only simple poles. And this is called Fuchsian in fact, the OPEs of product of vertex operators will give only Fuchsian systems. But you could ask yourself, if I start using spectral curve, I'm basically follow the same procedure as here. Start from a spectral curve which is non-Fuchsian, for example, having higher degree poles, or even things that are not even poles, like logarithms, dialogues, exponentials. A very nice one is we take 1 equals sine of square root of x dx. So a terrible singularity at infinity. But this spectral curve is in fact beautiful because if you apply topological recursion, what you find are the Weil-Petersson, basically these quantities will be Weil-Petersson generating function for Weil-Petersson volumes. And in fact, the corresponding theory is the JT black hole string theory. So, and in fact, by choosing other curves, also you can choose, as a spectral curve, you can choose the A polynomial of the knots. And what you will construct is basically the Jones polynomial. Right here. This is a conjecture which is not fully proved, far from being proved. But when you compute the numbers, it matches. Or at least we did it for a couple of nodes, and it works very well, like the figure I did.
Excuse me, and what's pxy? Maybe I don't understand. What is pxy equals 0?
So it's just an algebraic equation, a polynomial equation.
But y is a form.
Yes, but then the coefficients are K order forms. I mean, it's in
Y tilde.
base.
Probably should be Y tilde.
Yeah, Y tilde makes more sense. But then
No, you can also write it this way. It's also correct to write it this way, but the coefficients will be
for example, for this side.
Differential, cubic differentials, and so on. This is the way it does. You can do both. It's equivalent. I mean, if you are in CP1, you can. It's natural to do that, but you can do that if you are. But if you are not in CP1, then your other forms, and you can do both. And in fact, this is basically this is the spectral. So this is the this is basically the characteristic polynomial of. So basically, the idea is that you can extend this formalism to things that are non-Fuchsian, and then you are not going to define a local 2D CFT, but something more general. Typically, this can be a string theory. This can be basically this formalism extends far beyond local 2D CFT. Okay. But here, in this lecture, since I was asked to give a lecture about 2D CFT, let's focus on the Fuchsian systems. Also here, when I really write that, it means I'm in SLQC. But everything would work with, more or less with overlay algebras. Okay. So now So now what happens? So now the idea is that we choose a spectral curve, and the claim is that if we choose a spectral curve in that space, we compute these things, and they will correspond to the asymptotic, to some local asymptotic expansion of our amplitudes. This is the claim. Now, how do we compute topological recursion? And this is for that I show you this screen. Well, there is the definition of topological recursion. You find it, and it's a well-defined procedure from spectral curve that gives you forms. But we also start to exist some packages like Python or Python Sage or Mathematica that start to exist. I must say they are really not. I mean, the project is not completed. It requires task force if people are interested. It's just a matter of coding, on finding a good way to encode the data of a spectral curve and to do computations with it. For example, if you are in genus 1, you should have a good package of elliptic functions or something like that, and if you are in higher genus, or if you are even with curves that are not algebraic, what would be a good way to encode everything in a kind of universal way? This is, there are lots of questions behind that, but basically there exists a Python package. So this is PyPy, this is the website where you find all packages of Python. And there is an existing package. It is really, well, you see it's version 0.0 alpha 2, so which is really not far from, not pretty at all. In fact, the package works well for spectral curves that have only one branch point. But we started also to write it, and in fact there is also, in this package, there is also, this package is linked to a GitLab repository. I don't know those of you who are familiar with GitLab. There is a GitLab repository. This GitLab repository, you have to go to the branch that's called proper Python module, but you see there are also some other branches which are basically development branches. In this proper Python module, you have the module itself, the Python module, but you also have a Mathematica code, which is in fact the one made by Vincent Bouchard, which is, I think, the one that has circulated a lot and which is quite efficient. This one does not rely on only one branch point. It works with multi-branch points, even degenerate branch points. And it's Mathematica, but it has also some limitations, of course. But you can run on it, on the device. Yes, demo. In demo you have a demo. You see how it works. You should first install, import your module. Then how do you define a spectral curve? It works just this way. You define, for example, this is the Airy curve, so the simplest curve, which is basically y squared equals x, y squared minus x equals 0. Or this is y tilde in this language. So you see, it's parameterized as follows: x equals z squared, y equals z. The Berman kernel is just 1 over z1 minus z2 to the square. There is only one branch point which is at z equals 0, and the involution is z2 minus z in this curve. From that, you can start compute the omega gns. And for example, you just type S array omega gn 03, and it gives you this with this. It gives you a rational function, but in fact it's a form that you should multiply by dz1, dz2, dz3. And basically just to show you that it's more or less completely automatic. For example, if you compute omega 33, it's this big rational fraction. Okay.
How far are you able to go from?
I think I even computed things with genus, with this code like things with genus 10. For simple curves. As soon as you start to have not only numbers, but they are functions of some variables, it gets much, much slower. The problem is how to compute residues. In fact, either in Mathematica or in Python, the way to compute residues is not efficient. But I mean, it's just how it's really encoded in Mathematica or in Python, it's not good. It's not my fault.
In Mathematica, it seems that it's much easier to compute series expansion around the point and get
compute series expansion. But as soon as you start having things that depend on multi-parameters, again, it's not so efficient. I mean, if you have a way to make it more efficient, you're welcome.
Okay. Can you also use it if you don't have a global Galois involution?
Yes, and I mean, in fact, the definition of topological recursion only needs a local Galois.
Yeah, but can you use the program with only a local one?
No, it works with also local ones.
Okay.
No problem. So, I think we can now turn the computer off, just to show you that you can. So, if you don't want to learn how to use topological recursion, basically you can just press the button. When the code is completely developed, that is. Yeah, so yes, you can switch it off. Okay. So, in fact, so let me say we have our spectral curve. So let me now talk about topological recursion. Let me stop right. And in fact, most often I will write TR. Okay. And so we have a spectral curve, which is basically the data of, I mean, instead of writing an algebraic equation, let's formulate it in a slightly different way. Let's say we have a Riemann surface, which is embedded into the cotangent space of some of the base, star sigma 0, sigma 0. This map, let's call it X, so it's the projection map. And the map in the fiber is what we call Y. Y is the value in the fiber. And we have the data of a B, which is a 1 tensor 1 form with a double pole on the diagonal. And from that, TR is a procedure that defines some forms, omega GN. I'm not going to write the full definition of TR, but I will just give the first few. Omega 01 is just Y. Okay? Omega 02 is just B. So far, that's quite simple. I will write a formula for omega 03. Omega 03 is the sum over B equals branch points of residue when Z goes to B. So omega 03 is a 1 tensor. So in general, it will be where this belongs to, so each Zi here belongs to sigma. Well, in general, omega Gn will be a 1 tensor 1 form in sigma n, k sigma tensor n times, symmetric, and with some poles at the branch points.
Can you recall what is B?
B is a 1 tensor 1 form with a double pole on the diagonal and with normalized residue to 1. And in fact, you can, if I give you a choice of A cycles, there is a unique B that is normalized on the A cycles. And for example, in the torus, B is just the, so dz1, dz2 times the Weierstrass function z1 minus z2 plus the constant. The choice of constant is can be more or less arbitrary, but if you want it to be normalized on the A cycle of a torus, you should choose the G2 Eisenstein series. So if you choose G2, it's normalized on A cycle.
And all those forms explicitly depend on polarization.
Yes, I mean, B depends on the polarization, Y does not. B depends on the choice of polarization, or vice versa. B gives you
omega do depend on.
Omegas do depend on they depend on B, so they depend on the polarization. Now let me give you just the formula for omega 03. So sorry, this is for 2g minus 2 plus n strictly positive. Then the omega gns are n forms, tensor n forms, symmetric, with poles only at the branch points. Omega 01 and omega 02 have poles, but not at the branch points. Omega 02 has poles at coinciding points, and omega 01 has poles at the poles of Y, so typically the theta eyes. But all the others generated by this procedure have poles only at the branch points. And let me give you a value of omega 03. So you take B of ZZ1, B of ZZ2, B of ZZ3. So it's a cubic differential in terms of Z. So you shall divide it by a quadratic differential in terms of Z. In a local coordinate, you take dx of Z and d of y tilde of Z, where you have to use a local coordinate, but in fact this is a local coordinate independent. This is just the definition of, this is just the value of omega 03. So, if you are familiar with that, you may recognize that it has something to do with the Rausch variational formula. Is what? The Rausch formula is something that tells you how the complex structure of a curve changes when you move the branch points. In fact, this appears, the same residue appears in Rausch formula.
So here you wrote dy tilde, so it works for this.
No, in fact it works even if the base curve is not CP1, but locally you take a complex local coordinate. So it always works, but and it's independent of the choice of local coordinate that you make. Okay, so this is just an example. All the others can be defined in a similar way, and I'm not going to write the formula, but as I said, if you want, you just press the button, or you read the definition in the papers. So now, the important part for me is really that you get things that have poles only at the branch points. They are symmetric forms that have poles only at the branch points. And so now let me define the following objects. Wn, Wn of Z1. Maybe I should. Okay, let me a bit illustrate my curve. So this is sigma 0, and the curve here is something that has it's a degree. It's a cover. Okay, it's a cover of sigma 0, and the degree of the cover is the Q in SLQC. So it's a Q degree Q cover. So which means that if you pick a point X in the base, typically it will have several preimages. Let me call them locally as X1, X2, and 2XQ. The order doesn't matter, or let me say it in another way. The order is well defined only in some cards. In some, the order is defined only locally. But this doesn't matter anymore. You just make a choice. And remember that I want to define WNs that become on point on the base. Yes, this is what I did here. A point on the base and an element of a Cartan algebra. And let's take my Cartan algebra for SLN to be for G, let's say for GLN. Let's equal EI equals the diagonal matrix where you have 0 and 1 at position I, 0, and so on. The generators of the Cartan algebra of SLN are differences of EI minus EJ. The price must be 0, but these are the generators of the Cartan algebra of GLN. And let's define x1, E, I1, x2, E, I2, and so on. And everything depends on the spectral curve, so which is equivalent to the, which is what I wrote here, the parameters. The spectral curve is the depends on the alpha i's, the zeta i's, on the periods. Okay. Let me define it as the following formal for a series. Sum of g equals 0 to infinity, h bar for 2g minus 2 plus n, omega g n of, and let's take the pre-image x1 I1, xn IN. So that's my definition. If you want to have a value for another element of the Cartan algebra, just take linear combinations of these. So this is definition. This is a formal power series. Now this is not yet exactly our amplitudes, and as you remarked, there is a hat here, which corresponds to non-connected. And to define the hats, let me also define z equals e to the sum over g equals 0 to infinity h bar to the 2g minus 2 omega g0 of s, and omega g0s are just complex numbers. They are zero form. Okay. And let me define now w hat 1 is z w1, w hat 2 is z times, so it depends on two variables, x1, e1, x2, e2, will be z times w2 without the hat x1, e1, x2, e2, plus w1 of x1, e1, w1 of x2, and so on. W3 will be defined likewise, z times all the ways to split the variables into partitions, all the way to partition the variables, and this is called, well, basically, it means that the W's are the cumulants of the W hats, or vice versa, the W hats are the non-connected, the W's are the connected correlation functions, and the W hat are the non-connected correlation functions. So basically, the W3 will be the same thing, Z times W3 plus all possible ways of writing W1, W2 plus W1, W1, W1. I'm not going to write all of them.
W2, W3, you define Z, this is those ones.
So just, they are not normalized.
And these EIs, so sometimes you said the elements of SLN, and sometimes you said the diagonal elements.
Yes, they are in the Cartan. So they are linear combination of these. So here I define on the basis of GLN, but for example, to get basis of SLN, you just take differences. And in general, for elements in the Cartan, you just take the linear combinations of these that you need to make any element of your Cartan.
Is there some kind of generating function for those coefficients?
No, they are not so generic, like this one, for example. This is one of them. They have a lot of beautiful properties. And that's what I'm going to say now. So first, they have poles only at the branch point. On the other,
I mean, do you have some compact formal generating function for W hats in terms of?
Well, not so much. But they have plenty of properties, and this is what I want to focus now. So basically, this is our proposal. So the proposal is the following. We pick a spectral curve. By TR, we define these omega GNs by putting them as symmetrically defined WNs on the WN hats. What's the name of that procedure of going from connected to non-connected? Well,
Inclusion, exclusion.
Yes, exclusion, inclusion procedure. So from inclusion, exclusion, you get the W hats. And the claim is that the W hats are good candidates to satisfy all the axioms of a 2D CFT. But there are issues. One issue is that we know that omega GNs, they grow like 2G factorial. So this series is going to be divergent with Gevrey index 1. It may look like Gevrey 2 because you have a 2G, but the exponent of H bar is also 2G, so it's the factorial growth is the same as the exponent, so it's 1.
So it's factorial 2G and not 2 times G factorial?
Sorry?
It's factorial 2G and not 2 times G factorial?
Parentheses?
Yes,
yes, 2G factorial. At a given n. I mean, at a given n, it grows like 2G factorial. In fact, it grows like 2G minus 2 plus n factorial. It grows like very like. Okay, this you see that 2G minus 2 plus n seems to play a role because, in fact, these omega Gn are in fact related to some functions that compute some things in some moduli spaces, and 2G minus 2 plus n is very like characteristic of some surfaces. And that's why, in fact, it's called topological recursion, because the way to compute the omega Gn is a recursion, and it's a recursion on the Euler characteristic 2G minus 2 plus n. That's why it's called topological recursion. In fact, they have a meaning in terms of moduli spaces. The omega Gn can even be, can really be, so when you ask if there is a compact expression, it depends what you mean, but there is an expression that omega Gn is an integral over mg and mg, some mgn bar of some moduli space. Let me write it omega Gn of x. It's like Gromov-Witten invariance. So basically, they are kind of Gromov-Witten invariants with some forms on product of psi I equals 1 to n. In some way. There is a precise formula for that. It's even in the Wikipedia page. On lambda, let me call it lambda x. In the simplest example, lambda would be some Hodge class, for example. Or in fact, if you take this sign of square root of x, it turns out that lambda is the Weil-Petersson form.
But can you state the statement which you...
Well, I'm just somehow replying to the question of Eynard, which is there a compact formula for these objects? There is such a compact formula. The omega Gns are basically a generating function of Gromov-Witten invariance, but that's not really what I will use now.
But can you give some reference?
Yes, I mean, okay, I will give you reference later, but there is a huge now corpus of works on that. All the works of Shadrin, I would say.
No, they give examples, but it seems to me that you...
No, but there is a very general theory. Okay, in fact, this is not the point of my talk now. I just wanted to make the link to string theory.
Can you say what the x is in your modular space?
Yes. Basically, it's a moduli space of decorated Riemann surfaces, and the decoration depends on the data of your spectral curve. Okay. There are plenty of people who are really specialists of that here. And that's not the point. The point I wanted to make is now that, so my point is really that we have a proposal from a spectral curve build something that will satisfy the axioms of a CFT. And let me show you already that they immediately satisfy the OP onward. So let's see how these guys do satisfy OP onwards, at least as formal series. So as formal series, so OP as formal series. So where do the OPs as formal series come? So basically we have to ask ourselves, what happens, so how does W hat behave when two of the xi's come together? I should have written the formula for index 03. Omega 3 hat is z times omega 3 of x1 e1, x2 e2, x3 e3. Plus 1, just useful to do that. The omega 1 of x1 e1, omega 2 of x2 e2, x3 e3, plus permutation, plus omega 1, w1, w1, w1. Okay. It's a tensor product here, in fact. This product is tensor product.
So this is looking like this. There's no like small factorials which.
No. It's just inclusion-exclusion formula. So, how does W3, for example, behave when x1 is close to x2? This omega 3, this W3 here was the sum of was a series in H bar, which involves omega gn with n larger than 3. So it involves only guys that have poles only at the branch points. So this term has no pole. I mean, every coefficient in the H bar expansion of this term have no pole when x1 equals x2. So this will not contribute to the OPs, or it will be in the holomorphic part in the OPs. This term here, W1, also, the first term in W1 is the omega 01, which has poles at the punctured dies, but it does not have pole. I mean, basically, W1 of x1 does not know anything about x2, so it has no pole when x1 equals x2. The only term that could have a pole when x1 equals x2 is the term coming from W2 of x1 on x2. Okay? And because W2, the first term in W2 is omega 02 plus other terms that are that satisfy this stability condition. But so the only unstable term is omega 02. So basically we see that W3 hat of x1 e1, x2 e2, x3 e3. Well, let me give the generators ei1, ei2, ei3. The only singularity when x1 goes to x2 is the z times w1, so z w1 of x3, times the w2, and the w2 starts with an omega 02 of x1 in the i1 sheet, x2 in the i2 sheet.
So can you explain more slowly what you're saying? When we have poles, and so why formal like that?
Sorry?
So first of all, starting from that term, W3.
Yeah.
So what do you say when x1 goes to x2?
This term has no pole because this was a formal series involving only stable terms, and the stable terms have poles only at branch points or not at coinciding points. There is no pole at x1 equals x2 in any of these terms. Any in the h bar expansion of that term, no term have a pole at x1 equals x2. In the h bar expansion of that term, no term have a pole at x1 equals x2. The only term that can have a pole at x1 equals x2 is the term with, in fact, it would be this term with x1 e1. This is the only term. So here it was a tensor product, just to say that.
I just want to read the formula. Times W2 of x2, e2, x1, x.
But it's symmetric.
I understand.
Okay, let me write it this way. So where is this term with W3 hat? And now this has no pole, this one has no pole at x1 equals x2, because it's independent of x1 and x2. And now this one, it's W2, sorry, it's a W2. This W2 now is a series, which is here. It's a series whose first term is omega 0,2 plus stable terms. The stable terms have no poles at x1 equals x2, and only the omega 0,2 have a pole. So plus. Okay, so the only pole is that one. On that one, we know that it behaves like delta I1, I2, because it's only on the diagonal, dx1, dx2 over x1 minus x2 to the square. Which is this delta I1, I2 is also EI1, EI2. Well, this bracket is the King form in the algebra, or our scalar product in the algebra. Okay. So you see that indeed this is now this behavior is exactly the OPE we want for our CFT.
And also one more question. So the shape of this formula is crystal clear, but you also said this is inclusion. How is it called?
Inclusion, exclusion.
Exclusion. Why it's inclusion, exclusion?
Well, it's the general procedure of going from expectation values to what's called cumulant of expectation values, or vice versa. Or people sometimes call them connected correlation functions or non-connected correlation functions.
Okay.
So basically, the connected correlation functions are those constructed by TR, and the amplitudes are the non-connected ones, are the corresponding non-connected ones. And this construction guarantees that, in fact, you will have pole at coinciding points only if from the term omega 0,2, and this is exactly the OPE of your CFT. Now you have also, now we want also to wonder how does it behave, x1, ei1, and so on. How does it behave when x1 goes to, let's say, zeta 1? And now you have the same idea. It's in the connected terms. Again, all the stable GN have poles only at the branch point, so they cannot have a pole at zeta 1. The only term that can have a pole at zeta 1 is the omega 0,1. So basically, in this formula, the only term that will contribute to a pole at zeta 1 is the term that involves omega W1, and it's here. It's here. No, sorry, there is. So I should have written all W1 times this product of two W1s, but there is another W1 times the W2 of the two of us, so which together make the W2 hat. So if you think about it, it behaves like omega 0,1 of x1 in the I1 sheet times W2 hat of x2, x3, 3. If you think about it, this is, and now we know that W01 is Y. And we know that Y has a simple pole with residue charge. So it is indeed like dx1 over x1 minus zeta 1 with a residue which is exactly the charge alpha 1 E I1 on times W2 hat. And again, this is exactly the OPE you want for your CFT. Here I did the case of SLN or GLN if you want, but it works the same for all
This was the same. What did you say?
For overly algebras, it works the same way, except that you have to take different combinations of
What
these.
is the concept of spectral curve for Azali algebras?
It's the spectral curve of a Higgs field. I mean, use a Higgs field theory of how you get a spectral curve of each.
What is stress energy tensor?
Yeah, okay. The stress energy tensor now is when you take, so you will take now the finite part when x1 equals x2. So you take in the expansion at x1 equals x2, you have a double pole. Subtract the double pole. That's called the normal ordered product. And then take x1 equals x2 after subtracting. And make the Casimirs by taking the trace of the square of the alpha. So what is the stress energy tensor? So what would correspond to the stress energy tensor in our theory? Alpha 1 zeta 1 alpha n zeta n times T of x is by definition sum from let's say k equals 1 to q W2 hat of x E k x E k. So it's constructing the second Casimir, but normal ordered, which means that basically W2 at coinciding point, as we say, does not exist. So in fact, what you take is you take two different points, subtract the pole, and take the limit when x1 equals x2. So if you want, this is the limit when x1 goes to x2 of sum k equals 1 to q W2 hat of x1 ek x2 ek minus dx1 dx2 over x1 minus x2 to the square.
You should replace x2 by x.
Sorry?
You should replace x2 by x in order to match with
yes, yes, okay, that's right. x2 by x.
You don't have simple pole because you had the compound.
Well, and also because it's a symmetric form on
yeah.
Yes, but it's
central charge.
The central charge here is the, so in fact we are at q equals 0, which means central charge is the dimension of the Cartan algebra, so which is in fact here q minus 1. And for q equals 2 it means central charge 1.
Maybe you can comment on this if there is an explicit formula, because you have also something called determinantal formula, which is a kind of explicit formula.
In fact, I was going to do it in the last meeting.
Sorry.
So you're anticipating. So basically, yes, the reason why to make a sum, so it's just because sum over k of ek tensor ek is the Casimir C2. And basically, stress energy tensor is associated to Casimir, to the second Casimir, and over W algebras, generators are associated to higher Casimirs. It's the same. But basically, it's the same formula works for SLQ, and it will give you not only the stress energy tensor, but the W algebra generator. in any Lie algebra, in fact. Well, at least now, at the moment, all what I say is really valid only for ADE, but I will move also to BCFG. By the way, we didn't try to start from like a polynomial and with another Lie algebra and get polynomials for it works. That would be nice.
Can I ask one more thing? So this is a bosonic thing somehow inherently.
Well,
so is there some
in fact,
fermionic version?
there is a lot of boson-fermion correspondence that
Yes.
are involved. In fact, yes, these amplitudes are somehow, I mean, so basically the currents are bosonic, but the vertex operators are fermionics, and in fact there is a correspondence between boson-fermion that is very present in all this, and in fact you were talking about determinantal formula, and basically this is the fermionization of this, and I hope to have time to talk about this. So first we have a proposal that you see that the fact that TR gives you something that satisfies the OPEs onward. So the OPEs are almost trivial because basically they involve only omega 01 and omega 02, so they are almost trivial, the OPEs. Now the word identity, so how do you see that this is now a globally defined meromorphic form, this amplitude? So basically the word identity is just that when you compute this limit, you get a quadratic differential in X which is globally defined. And how can you see that order by order in powers of H bar? Basically, this is in fact almost the definition of topological recursion. Or vice versa, if you require that this is meromorphic to all orders in H bar, and see what it implies, and see, okay. In fact, topological recursion was invented exactly the other way around. Write that this is the meromorphic form of X to all orders in H bar, and solve recursively, solve these equations recursively, the word identities recursively, and in fact what you find is topological recursion. And so in fact it was invented the other way, so basically it's made to work. So this will satisfy word identities, almost by construction. Now, the fact that it satisfies the other axioms of the CFT is something which I think is not complete at the moment. We have almost all reasons to believe that it's working, but for that we need non-perturbative completion, and the program is not finished at the moment, but basically this is what we've been doing for the past, the committee has been doing for the past few years. For example, I'm sure that Koei Iwaki will present a case where we know how to do this non-perturbative completion. I'll just say a few words.
20 minutes.
A few words about the non-perturbative completion. So you see that at the moment we have defined the omega g ends of a given spectral curve in our moduli space. And in fact, the non-perturbative completion will involve all the other ones. And typically, I was labeling so just let me talk about the partition function itself. So remember I wrote Z equals exponential sum of h bar to the 2g minus 2 omega g0 of S. You see it starts with a negative power, h bar to minus 2 omega 0, 0, e to the omega 1, 0, and then there is a series. Let me write S. Well, this is a nice series, But exponential negative powers is not a series. It's called a transmonomial in the language of resurgence. So in fact, and I remind you that this grows like 2G factorial. With a parenthesis. So it grows like 2G factorial. So these series are divergent. And in fact, we already see that we have such a transmonomial. And in fact, to really define the full non-perturbative Z, let me write it this way, we have to do something like sum over series like that, over trans series. It's called now trans series, with trans series parameters. In fact, the other terms would be omega 1. Let me write this sum over G H bar to 2G minus 2, omega G0 of another curve S eta. And we have to take a sum over eta with a coefficient C eta. You can think of that as C etas are transitory parameters. In fact, to really get something that is going to be related to your CFT and which is a good completion, in fact, the etas, remember that the etas were the periods. In fact, you will want to take integer periods. That's strange. I mean, in principle, you could take an integral over the etas, but it turns out that the good choice is to have etas integers. Eta belongs to ZG. And the good choice is to take, well, let's say plus some eta 0. And the good choice is to take something linear in eta. So sum over I equals 1 to Q to G of rho I eta. Sorry, eta 0 is just fixed. Let me call it epsilon. So it's just the curve you started with, and then you shift the periods by all these permutations. And I believe that this is what Koiwaki is going to talk about. And if you make such a choice, which is called the Zach transform, so you have your series. This is the Zach transform. If you want, this is like Fourier series. This is like taking a Fourier series over the periods. And you do that perturbatively. One subtlety is that here you are taking the sum over ZG of something which was already a divergent series. It does not really make sense to take an infinite sum of divergent series. In fact, the good way to think of that is to invert, and so to write everything as series expansion, and each order make the sum over the periods. And then this is well defined.
Why do you have the sum over ZG lattice and not H bar times ZG? So why is this shift integer and not something proportional to H bar?
Well, I would say the simple answer is this is what works.
But it does not work. So for example, if you try to obtain some theta function, you will get not a generic theta function, but something with, I think, period matrix.
Okay, we can discuss that later. I just wanted to make it short here. And in fact, there are other proposals, but we know that this one works. And in this one, you get a tau function.
What is the role of rho i's? What is the meaning of?
It's some extra new parameters of your problem. If in the end this is going to be a tau function, it will depend on other parameters, and these are those other parameters. And you see there is the same number as the genus, so as the dimension of your Jacobian and all that, and somehow they can be parameters of a Lagrangian, so something which is outside of the data of the spectral curve. But this is common in Hitchin systems, and this is what you always have in Hitchin systems, or in tau functions. Somehow tau functions or Pavlov equation depend on some initial conditions, that are not in the equation, and there are extra parameters.
But why do you call it that transform if it is just Fourier series?
Sorry?
It's just Fourier series.
It would be a Fourier series if you would have really a function here. But since you don't have, since you have only formal divergent series, it's called exact transform in this
case. I know that what is that transform, it is a little different. It involves Fourier series, but...
yes. Yeah, I mean, okay.
And it's spelled with K.
I believe that Professor Koiwaki will talk about that.
So if I think of a non-perturbative condition, I would think of something that I can evaluate the finite value of the parameters.
In principle.
Could you repeat the question?
Yeah, so you say that if you have a non-perturbative condition, it will make a function that you can evaluate at finite h bar, for example.
So for example, if I want to take this Fourier series, I would do it, but in the h bar expansion, I would take, for example, the Borel summation, and then take the Fourier series.
In principle, you could do it. In practice, it's hard. No, you cannot reset h bar equals 1. At this moment, you cannot set h bar equals 1. Now, this is the last part of my talk, where I really want now to define a non-perturbative object from the determinantal formula. Okay, so basically there is a recipe to find not only something that perturbatively satisfies Ward and OPs, but which also has a more global meaning, and which hopefully are the conformal theory amplitudes. I just wanted to say a few words about topological recursion. Here are properties. And what makes it nice here is that the omega GNs enjoy a nice property. And in particular, they are related to quasi-modular forms. So, they have nice deformation properties. And the deformation properties are a little bit like cyber-Witten. Or cyber-Witten, basically they satisfy cyber-Witten equations. They also satisfy Miwa-Jimbo. And this is in fact an example of what's called special geometry. Another property is what I said, omega gn is some inverse or ngn bar or something. Okay, there are some Gromov-Witten invariants, and so on. In some sense, this reconstruction formula is somehow how to get from the Gromov-Witten invariance to the Donaldson-Thomas invariance or something like that. You would be able to make this all non-perturbative resummation. What other nice? Well, I mean, they have many properties, but the modularity implies that the holomorphic anomaly equation.
In which way?
With respect to a change of your symplectic basis of cycles. And in particular, this implies that this series will obey BCOV holomorphic anomaly equations, which is in fact the most efficient way to compute the H-bar expansion.
Which is what?
BCOV holomorphic anomaly equation, and this is in fact the most efficient way to actually compute the H-bar series. Okay, there are many properties and which are satisfied by any spectral curve, not only the spectral curve with Fuchsian type. I mean, it's satisfied for any spectral curve. So this comes so as you have a lot of geometry that is already included, which is very useful.
Bertrand, I have a question. So Z here, from the CFT side, it's just the correlation function of vertex operator, PA.
Well, with some subtleties of normalization.
Okay, yeah, but you don't have the insertion of currents.
Yes.
In order to compute the expansion in H bar, from TR to get omega G0 to some G, we need to compute omega Gn for higher n.
Yeah.
Now the question is, how do you see it from the CFT perspective? Why introducing currents, many of them at different points, allows to compute the
Yes, yes, if you want, it's related to the fact that morally, and this is not exactly true, but a vertex operator is, so morally the currents are the d phis. So morally a vertex operator, the alpha I of zi, is like e to the alpha I phi of zi. And morally the current is d phi. So you can recover the vertex operators by taking an integral of the current and taking the exponential. It's just morally true. It's not really precisely true, but somehow this is what this encodes. Okay. So yes. So now let me go to a non-perturbative model. And which, when you try to do its H bar expansion, you indeed recover TR. And this is the so-called determinantal formula. So I have only a few minutes left. I don't know if there is it.
Try.
There you are mentioning that this topological recursion maps to BCOV. The other day you were mentioning this refine. The other day you were mentioning.
Okay, I'm not mentioning the refine now.
No, but is it known if it maps to the refine of BCOV?
I think yes. I didn't do that myself, but I would say yes. I don't. My guess is that it does, yes. Okay. So in fact now start from moduli space of bundle of G bundle over sigma 0. G principal bundle. Here, by the way, G is a complex group. And together with a connection, and implies meromorphic connection. So let me take here sigma 0 is CP1, and P is the trivial bundle G cross sigma 0 cross CP cross G sigma 0, so it's the trivial bundle. But what will be non-trivial is nabla, which will be typically sum over, so D minus sum from I equals 1 to N of phi I over x minus zeta I dx, where phi I belongs to the algebra. So phi I equals 0. Well, which you can do only because you are in the trivial bundle of CP1, because so here they behave, I mean, this behaves like a Higgs field, but this is only because you are in the trivial bundle. Otherwise, this is really a space of connections. Okay, okay, take such one form, and such that the eigenvalues of phi I is alpha I. Or if you want, phi I can be diagonalized in this way: Vi, alpha I, Vi inverse, which in the algebra you should really write like that. So basically, you want to consider the moduli space again of Fuchsian connections with only simple poles on whose residues. The residue is not given, but only the eigenvalues of residues are given. And then this is a homogeneous space of a certain dimension, which is in fact the same dimension, G, the genus of the spectral curve. Okay, and now let's try to construct again something that obeys all our. Okay, let me take psi a flat section. So basically, it's d psi equals 0, or if you want, d minus. Let me put a 1 over h bar here. D minus 1 over h bar, or let me call that phi. So d psi equals, so h bar d psi equals phi psi. Okay, so which is equivalent to that psi equals 0, it's a connection. Let me define the following object, mxe equals psi of x e psi of x inverse, which in a general Lie algebra you should better write add psi of x e, where e belongs to your Lie algebra. In particular, you could choose it in the Cartan algebra as a special case and in a special subset of G. And the nice thing is that this M is a flat section of the adjoint bundle. So it satisfies the adjoint equation, which is h bar dm equals not phi m as a product, but a commutator. Which just means that it's a flat section of an adjoint bundle. I don't know if you know the nice theory of, these flat sections. And now let me make these definitions and I will finish. W1 hat of x1 e1 is just the killing bracket m of x1 e1 with phi of x1. W2 hat of x1 e1 x2 e2 equals m of x1 e1 m of x2 e2 times dx1 dx2 over x1 minus x2 to the square. And for higher n, for n larger than 3, let's write wn hat of these guys, x1 e1 xn en, will be the sum over permutations, so minus 1 I think to n minus 1, sum over all permutations sigma such that sigma of 1 equals 1 and sigma of n equals n. Product from I to 1 to n of x sigma I minus x sigma I plus 1. Product of dxi. And here you will take the bracket m of x1 e1 with m of x2 e2. No, sorry, x sigma 2 e sigma 2. Commutator with another commutator and until you reach m of xn en. And you close all commutators and close the killing bracket. These are the determinantal formula you were talking about. Now, imagine that you want to solve this equation in WKB series formally. So you find a formal solution for psi as a WKB series. You find a formal psi. You plug it here. You plug it there. And you can show that these guys do obey the OPs. They do obey the word identities. And when you expand into powers of h bar, you recover that the coefficients are the ones given by topological recursion. So this is the motivation. But now we have a way to also control the non-perturbative terms. And I should finish.
M is very non-unique.
Sorry.
M.
It is. I mean, it's really the definition. So you have to make a choice of one flat section, but in fact all flat sections are related just by multiplication by a constant element of a group.
But it's so not single-valued function, not single-valued function.
No, it's not a single-valued function, indeed.
But W is not single-valued.
No, W is not single valued, but when you start taking construction with Casimirs, then it gets single valued, and this is the word identity. Construction, the Casimir contraction.
WN is not single valued.
WN is not single valued. Currents are not single valued, but there are Casimir contractions, so the WN operators are single valued.
There shouldn't be hats.
Yes, there is no hats here. This is indeed the connected one. So I'm done. So basically, well, just to conclude, if you do the WKB series expansion, you recover topological recursion.
Okay, thank you.